Recording now. So the session is being recorded. Here we go. Okay, it's always worth mentioning. So the session is being recorded. Please be mindful and respectful of the class environment and your fellow students. Anything you say, type, draw will forever be recorded with your name attached to it. I'm going to allow audio as well, so I'm going to change the settings here. Session settings, I'm going to allow audio. So if you want to unmute yourself, you may to ask a question. And we'll get started. I want to do a little bit of review. I want to talk about the submission that was brought in. I know some of you have sent me emails requesting, oh, why did I lose a mark here? Why did I lose a mark there? That's fine. Let me explain kind of how I marked it, and some of those questions may be answered, and then we won't need to have a meeting. So I'm trying to reduce the number of one-on-one meetings. I don't want to meet with 40 students over 40 different things. That may in fact be the same. Okay, so I'll give you, I'll go through my file and some PDFs as to what I was looking for when I marked it. Okay, any questions about that so far? So I will go through the marking scheme and kind of the main points of how I marked it. Okay. All right, so here's my CAD file. Close that. All right, so here's my current CAD file. And I'm going to freeze out these drainage areas. Whoops, these drainage areas. Okay, so last day we did the storm sewer, sanitary sewer. Today we're going to discuss the sanitary design, and we'll get to that shortly. So the way I marked this is I had to first look at the road design, right? So I'm going to go back to the UCS plan. And if you look at the first 4 lines of the marking rubric that you received by email, you'll see I had some key station locations and some key elevations I was looking for. So if your horizontal alignment was correct, and that should have been correct or corrected after the first submission, and you followed along with what I did in the video or in class, then you'll see some key intersection and key location elevations. When it comes to Street A, I didn't mark Ledger Way. But when it comes to Street A, I was looking for the elevation at the start. So station 0 for Street A should have had an elevation of 194.692. If you didn't get exactly that, if you were off by a few millimeters, 1 to 2, even 3 or 4 or 5 millimeters, I wasn't too critical about that. But certainly this is the exact elevation of where Street A meets Ledger Way. Okay, so if you didn't get exactly that, then there might have been something wrong with the model you created for Ledger Way, the way you digitized Ledger Way from the PDF. Okay, so you had to have that elevation correct. Based on that, everything else kind of follows, right? So from there, we designed down 2%, down 0.5% to the low point, and up 0.5% to the first intersection at the end of Street B. So this intersection in plan is this location right here, right, where Street B ends at Street A. So we designed it on Street A, and the design elevation there is 194.718. So I was looking for that number or something very, very close to it. Okay, so that was another mark. And then I cross-referenced it, right? That elevation should actually be at the end of Street A, right? Because they're the same location. It's an intersection. So you'll see at the crown of the road, you should have the same elevation. Sorry. So you'll see the elevation 718, right? 194.718. That elevation should match this elevation. But as far as kind of a chicken and egg approach, this came first, and then we transferred, remember, from profile to plan, and then to the other profile. And that's how we started this location. This surface for the corridor, you don't really need it, but it's interesting to show that the elevation from the corridor is exactly where it's supposed to be when you're done. Okay, but you don't need to show that. You just need the design elevation. All right, so those 2 elevations match. And then at the other end, right, at the end of Street A, which was actually designed at the end of Street A first for where the low point on Street B is going to be, we can see the elevation here is 194.740. And that's the elevation of the intersection, not the low point, right? So that elevation is for this intersection here. So at that location, you should see that elevation. So the elevation again is 195.740, or again, within a few millimeters I allowed. And that intersection is right here. Remember, we have the high point here and a high point here, and somewhere in the middle, we have the intersection elevation. Not the low point, but the intersection elevation. So there's the 195.740, which is the intersection of Street A, intersection of Street B, or the first intersection with Street A and B. Okay, so that was 4 marks just to have, sorry, 3 marks, right? So we have 3 intersections, right? So I checked the elevation here, I checked the elevation here on both profiles, and I checked the elevation here on both profiles. And then one other thing I did is I checked to see that you digitized street B, Chuchmak, at this location here. Okay, so if this was correct, then I could assume the rest of it was correct. So that station value is actually, if you look on street B, is not at the intersection, but the first one in, and the elevation of that intersection is 194,881, and it's just part of the digitizing process. If that's correct, then I can pretty much assume that the rest of it was probably okay. So there was 4 elevations I was looking for, right? And they appear in a couple of different spots, right? So this elevation on both street A and street B, this intersection elevation both on street A and street B, and this intersection elevation on street B. So there's 4 marks for those values, okay? The station values had to be correct as well. It's really the vertical we're playing with, right? We wanted to make sure that the elevation was in the right spot. So yes, I looked at the station value, and that's noted on the marking rubric I gave back to you. But it was really the elevation that's critical for the profile design. So then that's 4 marks. The next thing I looked at, there was 6 marks now for the actual profile design. Now I looked at the key locations with the correct gradients, right? So on street B, you should have, right, down 2%, down 0.5%, up 0.5%. Then you should have through the elbow 1.1% approximately. Some of you may have gone a little steeper, but that's fine. And then this long tangent at 0.5% between the 2 elbows, right? The profile from here all the way to here should have been 0.5%. So I can check that. And then the elbow at the other end was going to be 1.1%. And then I looked at the design, up at 0.5, down at 0.5%. There's your high point. Okay, I didn't look at the elevation necessarily, but I looked at the profile. Then down 1.5, down 0.5, down 1.5, down 0.5 for the intersection and beyond. So the low point is not at the intersection, but at the projection of the gutter line. And then coming up and up from both sides with this intermediate 10-meter long 0.5% grade, so that we don't have any A value or change in slope that's greater than 1%. Okay, so I looked at that. And then on street A, it was a lot cleaner, I think, a little easier to handle. Down 2%, down 0.5%, up at 0.5%, and then continuing up at 0.5% till we get to the edge of pavement here, and then up at 2%. Okay, so I looked at all the slopes. Not so much the distances again. I didn't get too crazy with the station locations, although they're critical. But again, the relative gradient between the key points. Okay, so that was worth 6 marks. So if one of them was off, I took a mark off. If another one was wrong, I took another mark off. And once you lost more than 6 marks, then I stopped marking it. Right. So there's more than 6 slopes to check. But if you get, more 6 or more wrong, then there's so much to do there. You might as well start from scratch. So some people lost 1 or 2, but we're still okay. Now, again, as long as it's close, okay, as long as it was close, I gave some consideration, right? But the slope was really a value you had to type in. So if it was off, then I took a mark off. If it's wrong, if it's off a little bit, do you need to correct it? Technically, yes. But if it's close, I'll allow you to continue without fixing it. Right, so just make sure that your slopes and your elevations are within a few millimeters, or a 0.02% or whatever on the gradients. Okay, so I've graded this part of it, and if it was close enough, then I kind of let it slide. Okay, the profile is the bottleneck for the whole design. Without the profile, you can't do the corridor model, you can't do a corridor surface, you can't do your lot grading, you can't do your pipe design to get your top of maintenance hole elevation. All right, so what did I mark next? The next thing was the corridor model. So for the corridor model, I actually looked at the surface. So you should have created a surface to do your lot grading. So you should have a roads corridor model. And I created this style, and I inserted it into everybody's drawing, and I checked it. So here's what the corridor model surface looks like. Okay, at a glance, it should have no spikes, right? So there's a mark, no spikes. And then the other thing you should see, right? You may or may not have included Ledger Way. So you would have seen this pattern on Ledger Way, a low point near the intersection, a high point across the front of these lots or the back of these lots. And then you would have seen a nice smooth transition through the elbows and a nice smooth transition through the elbow here. This one, this elbow, I didn't ask you to model it, so this one should have kind of been okay. Okay, if you modeled this, if you did the widening on this, I didn't give any marks for that. I didn't take marks away if you did it wrong. I only checked this elbow and this elbow. So this is generally what you should see on your surface model. If there was a spike on the surface model, I took a mark off. If there was any error in terms of the information you used to build this, I took marks off. Okay, let me show you some common errors. Okay, so before you ask for a meeting, pay attention. Here's some common errors that people made, and I'll show you what it looks like on this surface if you do it wrong. Okay, so if you want to check this now, you can. I'll leave it up to you. If you go to the corridor model, and you open up the properties, the last two would have been the last thing you did, the two crescents, right? The crescent 2 and 3, the first one we're not doing. If you scroll over to the right, you'll see the targets. Okay, so for the targets for both are exactly the same. So let me show you the target for this region here. Okay, if you change the name of that one one of the sub-assemblies so that you can find it, the needle in a haystack, then I should be able to quickly find the one with a unique name, and the horizontal target is the original street B, the center line of the road, and the vertical target is the center line of the road profile. Okay, so I was looking for this and this. On the other one, it's exactly the same. The other elbow is the same. That little piece that you're going to extend to the center of the road, horizontally and vertically, you're going to the middle of the road horizontally, and the design profile of the middle of the road. So that's what I was looking for. Here was a common mistake, okay? And you might want to look at this. Some of you at least once made this mistake, some of you. Instead of using street B on this piece you identified, you had it on the one above. So if you did street B here, and I'll show you the effect on the surface, and you didn't do it here, so this was a common mistake, right? Oops, let me get rid of this, sorry. This, get rid of it. And then do the same with the vertical here. B, and then the vertical, street B, vertical, and I'll get rid of the other one in the wrong spot. So if you did your targeting in the wrong place, here's the effect you'll see. So you can check this quickly. You can look at the table. So if you made your targeting with the wrong piece, right, this is what the surface will look like. Okay? So watch the surface when I look at it in 3D now. Object Viewer, and you'll see some funny business in the, now it's not nice and smooth. There's kind of some wonkiness going on the pavement, okay? And that's a telltale sign that the corridor targeting link is wrong, okay? Some of them are more drastic than that, but that's basically the kind of thing you're going to see, okay? That kind of ripple effect, okay? Whereas you can see the other one that I didn't change is nice and smooth. All right, so that's the telltale sign. I look at the surface for that. I also look at the parameters, right? I look in here and I quickly go to the last two regions and I look at the target. You know, is the piece identified, the one with the target, with the correct target? And is the piece identified with the targeting? In this case, it's the correct targets, but the wrong subassembly is being used as a target piece. So that's wrong. Okay, I'm going to undo this a couple times just to get mine back to correct. So that was a common error. So take a look at yours and see if that was the case. Okay, if that's the case, it's an easy fix, right? Don't delete anything, right? If you have your targeting the wrong subassembly, just take it away, right? Take it away, delete it, and then add it to the other piece correctly. Okay, so that was a common mistake. So most people got 4 out of 4 on the first part of the corridor marking, but didn't get 4 out of 4. If you got 2 out of 4, this was probably the problem, a targeting issue. It's very subtle. It's not going to make a huge difference to your design, but in those corners, you might get the wrong top of the maintenance hole elevation, which is going to have an effect on your pipe invert elevation, especially sanitary when you're starting at the top end, right? So that's something to be mindful of, okay? So if that was a problem, if you didn't get 4 out of 4 on the second part of the corridor with the targeting stuff, that's probably the mistake you made. All right, so that was a common error. The next part, I believe, was the grading. I started to look at the grading. You should have had, and I'll show you mine. If you go to the point groups, you should have an existing ground. Show you here, properties. You should have, whoops, I didn't do it, but I will right now. So I'm going to create a new one, I'm going to call it existing, e.g. I'm going to make it look like a point, and I'm going to call it elevation only, whatever the case might be. And everything that goes in there is called existing. I can't remember if it's EX or EG. I think it's EX. Oops. No, it's probably EG. Include EG. There we go. All right, so what do those look like? There's some layers that are frozen or off. Okay, these layer names are wrong. Okay, I wasn't too picky about the layer name, but I gave you the layer names for these. If we look at this, you'll see the different layer names. So there should have been a layer. Let me turn this off. There should have been a layer for the existing points. So these are the imported points. These are the existing, right? They were imported from the CSV file I gave you. So you can see that they are in the primary group EG and the raw description is EG. So those are on their own layer and they have their own group, right? So this layer is existing. Again, I'm using a short name here. You would have C road existing or C road proposed, right? So make sure the layer names are correct. Again, I wasn't too picky about the layer names. I was more interested in you had different layers than the layer name, okay? But I don't see why you would have a different layer name than the one I asked you to use. I'm not using those layer names, okay? So I'm being a little bit sloppy, but this is what I was looking for. So then I checked the layering, right? So I turned off this layer. They should be on their own layer. These interpolated values should be on their own layer. Everything at the front lot corners where the corridor elevations are going to be taken, that should be on their own layer. And then there should be a layer for all the grading you did. So everything in yellow. So those are the different layers I asked you to produce. Existing, proposed interpolated at the rear, proposed from the corridor at the front, and then proposed lot grading somewhere in between, right? So there was 4 layers. But there's only 2 groups. There's a group for proposed, FG, and a group for existing, EG. So this is in one group. And these 3 different layers all have the same description. They're all in the same group. So if you list them, you'll see FG is the description, FG is the description, and FG is the description, and they're all in this group. So 2 groups, existing and proposed, but 4 layers. 1 for existing and 3 for proposed. Okay, so I looked at that. So those were the 3 and 3 marks. If you look at the breakdown of the marking, right? Did you create the layers correctly with the correct, the color wasn't a big deal, but different layers. And then I looked at the different styles that you used. It should have been 2 decimal places, elevation only. And then I also looked at the group definition, right? Making sure you had the right style, the right text height, and so on, okay? So that's where those 3 plus 3 marks come from. All right. The next thing to the lot grading. Now the lot grading, it says there's 10 marks, but the one before that is the design of the rear yard back here, right? I gave you some guidance on how to design this. The design for this will only work out if the elevation here and the elevation here is correct, or at least close to what they should be based on the corridor model. Remember, these 2 elevations come from the corridor model. So if the profiles are wrong, the corridor is going to be wrong, the corridor model, the surface is going to be wrong, and then these 2 elevations are going to get the wrong vertical data. Okay, so these didn't have to be perfect, but they had to be close. Otherwise, you wouldn't be able to design the backyard the way I described it to you in the PDF. Okay, so if you did that, then I would see, so I gave you 1 mark for that, and then I gave you 10 more marks for everything else. But I marked, so really it's 11 marks, and I looked at your surface, okay? So if you created the surface for me, great. If you didn't, I did it myself. So I was just trying to streamline the process. So you were expected to create a surface, and this is all I wanted you to do. Create a surface, call it FG, and add the point group FG to it. That's it. No editing, no boundary, nothing, right? And I'll do it right now. This is how quick it goes. Create a surface, give it a name, say okay, and once you have that surface, assign the point group called FG. That's all you had to do. That was it, okay? And then that surface, I can look at it and visually see if there's any problems with it. Let me show you what mine looks like, and you can compare it to yours. I'm going to delete this one. Okay, so that's all this surface is. There's no editing on it, right? It's just a surface with points. No boundary, no break lines, nothing. We will modify this surface when we do the cost estimate, when we do our earthworks volume calculation. But at this point, it's not critical. Okay, so that's why I just said build it. I could have built it myself, but I figured it was faster if you provided it for me. What I did do is create this style. I call it check. This is a contour every 0.1 meters, and it's, I believe, I don't think, is it vertically exaggerated? I think it is. It's vertically exaggerated 5 times. Okay, so if you create this surface, here's what it looks like. Object viewer. So you can see here, see this pattern here? Okay, I know that they look like squares, but they're really kind of a circular pattern. Those show 1, 2, 3, 4 low points in the backyard where the catch basins should be. So I look for that. And that's the 1 mark I'm looking for. So make sure that you designed that rear yard, backyard correctly. Okay. At the north end, you should see this pattern, but half. Right? There's a low point here. You can kind of see them circulating. They would go around through the other subdivision to create this pattern here. So there should be a low point here, 1, 2, 3, 4 low points at the top of the site as well, right? So this was 1 mark, and then I started looking for these patterns. You need to see 4 low points up here. The grading across the road should be flat, so I should see this pattern here, flat across, which means there are no center line elevations on your surface. Okay, it's modeled flat across, and I'll discuss why again. We did it in CDA, but I'll discuss it again when we do the cost estimate. And then you should see kind of a arrowhead pattern. This is the high point right here. See this line here? This is the high point. You can kind of see an arrowhead pattern through here. This is the high point, and there's an arrowhead pattern right here, and it's more obvious on this side. Okay, you can see here the high ridge. These are the split points, right? So water drains this way and water drains toward the road this way. So that's your split point all lined up through here, okay, on these lots here. And then if you did the details, you would have had a little bit of back splitting here. So you would have seen a little bit of a 3-to-1 slope across here somewhere, something, okay? It was a little steeper than 3.5 or 4% in here, so there was a little bit of back split to do here. So that's what the surface looks like. It should have no spikes. It should have anything unusual on it. That's what your surface should look like. So if you look at yours in 3D and you don't see kind of what you see here, if there's anything kind of odd out of the ordinary than what you see here, I started taking marks off, right? If the split point was missing, I looked. If this was missing, I took a mark off. If I didn't see these 1, 2, 3 low points for catch basins, I took some marks off. This was worth 1 mark all by itself. And then I made sure that there was the high point ridge and so on, and the pattern on the road. So this is what your surface should look like for the most part, okay? Is it complete, ready for earthworks calculations? No, not at all. We're gonna do some minor modifications to it, particularly on this side here. There's actually missing area. So if you look at the surface, it kind of ends here. We need to expand it all the way here. So if you look at these together, object viewer, you'll see, there's a missing piece here, right? So we have to fill in the blank. And we'll talk about how to do that before we do the last submission. All right, so that's what I was looking for. So this was, like I said, it's worth 10 marks. And if there was something wrong, I took a mark off. If there was something else wrong, I took a mark off. And every time there was a little bit of an issue, I started taking marks off. Okay. Now, some people ask me, well, if I didn't get 10 out of 10, can I continue? The answer is yes and no. Okay. And it really depends. If it's a minor error, okay, like if the spike isn't huge, if it's within range, then you might be able to leave it. Okay. But if there's a huge spike coming up or a huge spike going down, right, 0 elevations or something high because you got a decimal place wrong, it's a lot more critical. Okay. So I can't speak to all the possible things that went wrong on this surface if you did it wrong, right? Here's some common mistakes, right? Sometimes you have a point, right? You might point somewhere. Maybe you used a point for here, end point, that you're going to use to project, right? And the elevation of this happens to be 0, right? So if this happens to be 0, if you didn't use an AutoCAD point, but you used a Civil 3D point, and it's got an FG description when you update your groups. If you look at this in 3D, object viewer, it has a 0 elevation, you'll see this spike. So that's a common mistake, to use an elevation with a 0 elevation. So that's a common mistake. Another common mistake, and you can watch this happen on the fly. Remember this, if even here might be better. Remember this, I'm gonna just check using the inquiry tool, inquiry, list slope. So if I go from node to node, this is up at 2%, And if I go from node to node, this is up at 2%. So this is a high-low of 2%. Well, if you did this by mistake, high-low, from the front node to the back node, whoops, do that again, node to node. And instead of typing in G, you type in S, enter, 2 to 1, S, 2 to 1. You'll get a solution, right? But look how much higher it is, 203 versus 295. And it'll fall if you offset 8 meters within the building envelope, 12 meters. So in plan, you might not notice that's a problem if you don't read the elevation, right? Or if you don't know what the right answer should be. So if you leave that, watch what happens. Update. And if you look at this in 3D, then you'll see this kind of mound. Forget that, right? You'll see this kind of pyramid, right? That's 2 to 1, not 2%. And you might see a little bit of a problem. And you can also tell by the density of contours and so on. Okay, so that's another common mistake, to use a slope instead of a percent grade. And it makes it steeper. Okay, so that was another common error. So those are the general things to look for. Another thing that happens, and again, the surface is important, but really the data that creates the surface is important. So one of the things that could happen, let me just update this. One of the things that could happen is you might have created these points, but let's say the description is wrong. Right? And this is why I checked the point group in the description. Suppose the description, instead of being FG, is EG, then they're not on the surface. So here's another common mistake, right? If I update my point groups, now they come off the surface, and now you don't see object viewer. Right? You start to see something funny in the backyard here, or if this is again the wrong description. You can see it when you bring in your 10 lines. Watch. If I turn on my style and I include the 10 lines, the triangles, right, you'll see that there's no vertex there. These points are designed, but they're in the wrong group. They're not on the surface. And now your surface is wrong. Okay? So those are some minor issues. Again, you should correct those, but they wouldn't have significant effect on your design, on your earthworks analysis. Okay, so please review your own based on this discussion, and make sure that if one of the issues is something I've described here, I think I've given enough examples of common mistakes. If those are the things that went wrong, take the time to correct them yourself. Okay, I'm trying to avoid, like I said, meeting with 40 students one at a time. If you can see the kind of issue you're having through this discussion, I expect you to be able to fix it yourself. Okay. Any questions? Anybody have any comments or questions so far? We'll talk about the drainage areas next. And remember, if you want to ask a question, you can unmute yourself. You can ask instead of type. Oh, there you go. For the corridor, I got 4 out of 4 for street A. For B, I got 3 out of 4. And I checked both the common mistakes that you mentioned, but I see that they were correct as what you said. Are there any other mistakes? Did you look at the surface? T, did you look at the surface in 3D for the corridor model? Were there any spikes on it? No, okay. So if you can't figure it out, then maybe we should have a meeting. Okay, we can look at it together. So there must be something either missing or wrong that we haven't picked up. Could be the extent. It could be some overlap, right? Did you have overlap? Remember how the corridor pieces shouldn't overlap each other? So that might be something else to look for. Remember when you model it, I'll show you mine again. Again, these are other things I look for. So if you go to the corridor and you look at the corridor, when you look at the corridor, and I mean in 3D, it helps isolate it, right? The pieces should not overlap. There should be a gap between the pieces, right? Make sure they don't overlap. That might cause a problem. And the other thing I look for, like I said, sometimes you see a spike at the beginning or at the end, or at the beginning or at the end of the corridor model. Because remember, the horizontal range is greater than the profile range. So you get 0 spikes at the beginning, at the end of every alignment, including the gutter alignments. Okay, so there should be no spikes. And that's reflected on the surface. If there's no spikes on the corridor model, there won't be any spikes on the surface. Okay, so those are some other things to look for. I thought I addressed those when I was showing the modeling, so but it's still worth mentioning now. So again, T, if you can't figure it out, email me. So any email requests prior to today, I'm ignoring. If you want a meeting, send me the email. Okay, so send me an email and I'll set up a meeting. All right, so that was the drawing and how I marked the drawing. And then I looked at the drainage areas. So the drainage areas for sand and storm were 5 marks each. Then the breakdown was 3 and 2. The first part out of 3, I looked at the drainage areas, make sure you delineated them properly. And then the second, the 2 marks, I looked at your layer control and some of the things that you should have in the drawing. Okay, so let me show you some PDFs. I just pulled some examples. There's no names on these. Okay, so I just looked at some drawings. So at a glance, I look at these, right? The entire area is covered, good. There's information for each area, good. The delineation, right, is always between pipes, right? So if there's a maintenance hole here, these 2 lots drain to this pipe, and these 2 lots drain to this pipe, so there's the drainage divide. Here's one common error. See this? This is in the wrong spot. This unit and this unit both come out this pipe, which connects to this pipe. So this divide should actually be right here. Okay, so that's a common mistake. So dividing between units incorrectly. Okay, the rest are okay, but that one's wrong. So I would have taken a mark off for that. The other thing I'm looking for is the drainage bubble. Make sure you put in an area. See, so technically here, somebody forgot to label this little piece that's going to go the other way, which is critical for the analysis, right? Is that too big to go the other way? We proved it's not. So you should label each one. So I might have taken a mark off for missing bubble data here. These pipes, this one and this one, had to be divided into 2 parts, townhouses versus singles. So that had to be present. So that was most of the design consideration. Did you draw the division lines in the right spot? Here's another error down here, right? This line should actually be here because these 2 units drain through this pipe connecting to this pipe. So this line should be from here to here and then down this unit. So this is drawn in the wrong spot. Okay. Otherwise, it's not bad. At a glance, it looks good. Now, again, remember the discussion we had last week on sanitary sewers. It doesn't matter what you do here. It's not going to change your pipe sizes, right? So if you make a mistake here, it's not going to impact what you're going to construct. However, it's embarrassing. You need to make sure that this is delineated in a way that's representative. Okay, so this one is drawn in the wrong spot, and this one is drawn in the wrong spot. Okay, but at a glance, everything else seems pretty good. The other thing you want to show here, and this is where the other 2 marks came from, sanitary information only. So I shouldn't see any grading information. I shouldn't see any sanitary information, storm information. I shouldn't see any water main information. And other stuff that really doesn't matter, right? No driveways and so on, right? Keep it clean and simple. So at a glance, it looks correct. I would have taken at least 1 mark off of here because somebody forgot. They turned off all the sanitary and water main information that's proposed in the subdivision, but they're still showing the existing stuff. This is water main. This is a catch basin. That's storm. This is the storm sewer right here. This is the water service. So everything related to the other services, not sanitary, should not be showing on this drawing, including the existing stuff, and that's a common mistake. So you forgot to look at the hydrant. That's a water main thing, and so on. Right? The valve chamber. That's a water main thing. The valve box, that's a water main thing. The catch basins, the maintenance hole for storm, that's a water main. That's a storm thing. There's no grading here, that's good. But existing storm and water main is present, I took a mark off. Okay, so that's the kind of rationale I was looking for here. Did you delineate correctly? Did you put in all the drainage data, right? All the bubbles with the areas and the populations? And did everything get cut up properly? And then for presentation's sake, did you show only what is meant to be on a sanitary drainage plan, i.e. no grading, no storm, no water main, existing and proposed. All right, so this was where 3 marks for kind of the design delineation and data, and then 2 marks for the drafting. Did it look right? Okay, it's very, very subtle. And again, most people got at least 1 out of 2. Some people got 2 out of 2, but that was a common mistake, forgetting the existing non-sanitary stuff. which was the same common mistake on the storm. Okay, so you can change that if it's a problem. Okay, now again, is it going to make a difference to your design of the pipe sizes and slopes? No, not at all. It's not that sensitive, but you should correct it. Because at a glance, it doesn't take long to see if you know what it's supposed to look like. It doesn't take long to see whether there's something that really doesn't make sense, right? And this is a big problem, right? This is wrong and this is wrong. Okay, this is a drafting thing, but it's sloppy. But these two are critical. These are big issues that in my opinion, I would deem embarrassing. You shouldn't do that. It doesn't make sense. Okay, and then there's data missing here, right? There's that one drainage bubble missing here. Okay? And don't forget townhouses versus singles and so on. Okay, any questions about the sanitary? Does these affect the design sheets though? It'll change the input data, right? So this area is going to get a little bit bigger and the population might change. This area is going to get a little bit smaller and the population might change. So the design flow, sorry, the expected flow to change, but it's still going to be less than the pipe capacity that you already have. So it's not going to change the design. If you already drew the sanitary sewer in the profile, that's not going to change. It's the details on the design sheet that are not going to match. And what happens when you send this in for review, they want to see that the information on the drawing is the same information that's on the spreadsheet. It has to match. And if there's something on the drawing that's different than the spreadsheet, they're going to flag that and say, hey, what's the problem here? Which one's correct? Right, so if you change the drawing, which you should, based on these two errors, right, I would update these. So this bubble here and this bubble here are going to be affected. And if you change this one, this bubble here and this bubble here is going to be affected. Right, you're going to change 1, 2, 3, 4 areas and potentially 4 populations on your design sheet. They have to match. If they don't match, whoever's reviewing it is going to flag that and say, hey, what's going on here? What were you thinking? Why doesn't it match? Because it's this information that determines your expected flow, that then determines your pipe size. Okay, and that is critical on the storm, not sanitary so much, but on the storm sewers. Does that answer your question, Stephen? Okay. Okay, so if there's no more concerns or questions about the sanitary, let's look at the storm. All right, so we'll look at the storm. Storm was very similar. I looked at the drainage areas. I should see 1, 2, 3, 4 areas for rear lot catch basins proposed here. So there should be 4 areas. And there should be 4 areas up here that are related to the catch basin. There's a catch basin here, a catch basin here, a catch basin here, and a catch basin here, right here. Okay, so if you look at Chuchmak close, you'll see a catch basin on all of these block delineations. All right, so there's the area that drains to this catch basin. There's the area that drains to this catch basin. There's the area that drains to this catch basin, and so on. The high points, these division lines, are based on the elevations you visually review across here. So if you look at the grading plan, you'll see where the elevations are high. And they're always between these lines. These are the low points. So somewhere between these lines along the backyard is going to be a high point. Somewhere between these 2 catch basin locations is a high point, and so on. Somewhere between these 2 catch basins is a high point, and so on. And so if we go back to the drawing, you'll see that. And I'll show you my sanitary, my storm drainage. Storm drainage proposed, I believe. No. Storm DR, where's my storm? This one, where's my storm? Oh, maybe I froze it, sorry. Storm drainage. Okay, so these are my drains. So I color coded them in blue, right? So this area here goes to this catch basin, and this area here goes to this catch basin, and this area here goes to this catch basin. So how do I know where the high point is? Yeah, let me turn this off. Right, so this is a low point, 74. This is a low point, 97. And if you look between here, you should see an elevation that's higher than everything else, right? So this is 505, 512, 526, 530, 520. This is the high point. So that's the split. So it drains this way and it drains that way. So you have to kind of visually look at the elevation, see which one is highest. So that's the high point. If I turn on my division lines, my drainage area for storm drainage, you'll see a division line exactly there, right? So it's not a coincidence that this line is exactly where this point is. Similarly here, right? So I know there's a catch basin here, 74. I know there's a catch basin here, 451. And if I do a visual inspection, 489, 504, 508, 498. So this is the high point, and that's why that division line is there. Okay, so that's the split point, and so on. Okay, so you kind of have to look at it. There's a division line right here, right? So this drains to the catch basin. This backyard drains to the road and into the street catch basin. So there's a little area here that goes into the existing road. All right, and then at this end, right, I know there's a catch basin here, but I have two different areas. This area is single detached homes, and this area, this little piece, is townhouses. Okay, so I have one at 0.5 and one at 0.75. Now, this 0.75 is so small that I could just make this 0.07 at half, or I can be conservative and say 0.07 at 0.75. I can treat this piece as a townhouse along with this piece and be conservative and send that area to the north. And if that works, then certainly I know this is actually smaller. It'll be fine, right? But technically, there should be two areas that drain to the catch basin that's right at this location here. Okay, what catch basins am I talking about? Some of you might be wondering. Let me show you the catch basins we're talking about. If we look at Chuchmont Close in the plan profile, right, I'm talking about our site is down here, right? So there are catch basins, 1, 2, 3, and one right in the corner here, 4. Those are the 4 catch basins that we're going to drain through. Our backyards of our townhouses are going north through these 4 pipes. Okay, so that's what's happening. So those blue areas, those dark blue areas, are all draining to the north. Everything that's green is draining through the site. This thing here and this thing here is draining to this existing pipe system. And then we're also going to look at, are these backyards allowed to flow into this road and into the pond here? Okay, so we'll look at that. So potentially we're only designing for the blue, the internal green stuff. Okay, I'm going to assume that these are allowed to flow out here, and then we'll check it and see if it's true or not. All right, any questions so far? All right, so the delineation, and let me show you this with the grading, and this is part of what I was looking for. When you look at the surface for the finished ground, right, you should see, I'm going to select similar and select the surface, object viewer. You should see a drainage divide everywhere there's a split point, right? So these are the split points, right? Backyard's going this way, the front yard going toward the road. These are the areas that delineate the drainage to each catch basin, and this is going toward the road. This is going toward the road, right? You can see the areas here, 1, 2, 3, 4, and the drainage divide. These go to the backyard, these go to the front yard, and so on. So I can quickly look at it in CAD, okay? But I have a sense of what the pattern is, so I only really need to look at the drainage patterns. So you can see how the high point or the split point defines the drainage divide between the front and the backyard. And then you'll also see where all the maintenance holes are. I know there's a maintenance hole here. I know there's a maintenance hole here. I know there's another one here. There's one at the intersection here. There's one here. And then there's one somewhere out here. This is a dead end. And somewhere out here, there's a dead end. Okay. So that's what the drainage areas look like. And again, if we go to the PDFs, right, I would look at the drainage areas. I would identify 1, 2, 3, 4. I would identify 1, 2, 3, 4. This one's made up of 2 areas. That's good. The entire site is covered. There's a perimeter kind of overall boundary. That's good. And then I should see where the maintenance holes are. 1, 2, 3, 4, 5, 6. And in here, you may or may not have a drainage area for each single pipe. And this is true for sanitary as well, right? I would take, if you look here, there's the pipe that goes from here to here. And we take the entire area of these 2 pieces and put it into that pipe. This maintenance hole, all it does is take this pipe and change its direction. So I would take this little piece and just have a 0 area, 0 infiltration or whatever it is, whether it's sanitary or storm, and just pour everything into the pipe upstream. And then this has just got nothing tributary to it. Everything, all of this is flowing through here. And the purpose of this little pipe is just to change direction. There's no additional area or flow coming into it. We still need to design it. And basically what will happen is whatever size and slope of this one, this will be exactly the same, because there's nothing more going into it. It's all the previous stuff. So we're just pouring into the top end and assuming it goes through. Okay. The other thing I asked you to look at is chopping up the backyard here, right? And the drainage divides at the back were going to be based on, this is somebody else's, right? They were going to be based on the drainage divides that we have out here. 1, 2, 3, 1 out here. There's a high point on Ledger Way. Then there's an area here, and then another area here that this little backyard could be tributary to. Again, it's more sensitive than sanitary, but it's not that sensitive, right? So if you draw one line a little bit here, a little bit there, these areas are in hectares, right? In hectares. So to change this by one number, to make that 0.13 or 0.11, to change that represents 100 square meters, right? 0.01 hectares is 100 square meters. So again, the area really isn't, it's not that sensitive because at the end of the day, they'll still all add up. So you might get one pipe a little bit off in its expected flow, but then the next, it'll be accumulated to the next piece, right? So if you add a little extra to here instead of here, right? If this is in the wrong spot a little bit, eventually both of these areas are going to be added together to get the pipe down at the end, right? So eventually it kind of takes care of itself. So it's more sensitive than sanitary, but it's not that sensitive. Okay, so there's a lot of leeway here as well. Again, there's different runoff coefficients for the townhouse area versus everything else, which is single detached, right? This is 0.5, and up here we have 0.75, so I looked for that as well. And then the last two marks for this was, did you show just storm information? And you can clearly see here, no sanitary, no water main, and no grading, both proposed and existing. So that's a nice, neat. So this would have been marked 2 out of 2. Right? And then there was an effort here to divide the backyards. I would have given probably 3 out of 3 for this one. If we go back to here, they didn't do anything with the backyard. They left this area all one piece. So I probably would have taken a mark off for that and so on. Okay, so those are the drainage areas. Again, 5 marks, 3 for the technical part of it and 2 for kind of the drafting consideration. All right, any questions about that? I know I'm spending a lot of time on this, but I'm trying to reduce the number of one-on-one meetings that people might request. Okay, so I hope I've answered a lot of the questions regarding your own submission. And hopefully if there's any changes you need to make, I've given you enough direction. If you're honestly, if you can't figure it out for yourself, that's when you want to have a quick one-on-one meeting with me. Okay, so if these aren't the problems in a general sense, then certainly send me an email and I'll set up a meeting. Some more questions here. Let me just read the chat. Oh, sorry, my volume was off. I hope nobody was asking verbal questions. My headphones were muted. You're saying that we can have the drainage from manhole 2 to manhole, including manhole 1 and 3. That's what I have in my design. Yeah, that's fine. Yeah, so this area here, right? This pipe here, just have a 0 area and take all of the area into this pipe and it'll just flow through. So whatever this pipe size and slope is going to be, this will probably be the same. If we're missing a point in the delineation for storm, do we need to correct it? It depends how critical it is, right? Are you talking about a point, like if this point was missing and you went straight across here, like that, Warren? I'm just missing the 0.5 hectare on the right side. Over here. Sorry, this is the left side, over here. You're missing this. Yeah, so if you took yours straight across here, if your polyline goes across here, that's fine. As a matter of fact, if you do that, I would just take this area and this little sliver here and make it all one and call it townhouse. And that's conservative. Yeah, so there's more than one way of doing it. Again, at the end of the day, the pipe sizes you're going to determine, one way or another, are going to be very similar to everybody else. right? The details will be there. Like you might have a slightly different flow, but the pipe size and slope you're going to select are basically going to be the same as everybody else's. The expected flow may be significantly different, but they will all result in the same pipe size, right? The pipe capacities are all going to be the same. The expected flow based on the drainage areas might all be drastically different, but they'll all be less than the pipe capacity. So you'll all have the same pipe sizes and slopes for the most part. You'll just have different actual flows depending on how you drew your drainage areas. Does that answer your question, Warren? I hope. Okay. Any other questions about storm? Okay, so there's still quite a bit to talk about now in terms of how to design the storm sewer. It's significantly more involved than sanitary. When I move the profiles and corridor to adjust for the height of the sewer labels, I needed to update the corridor. Does that affect anything? When I moved the profiles and corridors, if you change your assembly, you have to rebuild your corridor for sure. And if your corridor changed and it affects your front lot corners, then you need to update all of your lot grading. So Stephen, if all your front lot corners are now going to be different than what's on the surface for the roads because you changed the road assembly, I just moved. Oh, what do you mean you moved it? You took it. If you move, you took it from here and you put it over here. Was that what you did? Stephen, is that what you did? You moved this? You picked it up and you moved it? I had my profiles too close to it. Yeah, so if you move this stuff, yeah, but if you change it, right, moving it, that's fine. But if you change it, if you change the slopes or the widths of any of the pieces, that has an effect in your corridor. But moving it doesn't. So if you put this over here, that's not going to change your corridor, right? No, if you're doing exactly what I just demonstrated, then no, you're fine. It's if you change this, if you change the width or the slope, or if you take away one of the subassemblies or add another subassembly. If you change the geometry, then it's a problem. If you just move it, then it's fine, including the profile, right? If you move the profile, if you take the grid and put it somewhere else, that doesn't do anything. Yeah, it's only if you change the details, yeah. Okay, so now let's look at what you need to do with the information you provided. Okay, so let's look at interior to the site. And I'm going to show you on the drainage areas that we have for the site. So let me look at this. And let's look at the drainage areas for the site. So if we go to storm drainage areas, if you look at this, you'll see to design this pipe here, right, you don't see an area for this pipe and you don't see an area for this pipe. The rear lot catch basins don't have their own tributary areas delineated, right? So there should be an area for this rear lot catch basin, an area for this rear lot catch basin, and an area for this rear lot catch basin. So they've watered it down, they've simplified it, okay? And I'll show you why they do it, okay? Let's look at our drawing. So on our drawing, right, if I bring up the storm sewer, let me just isolate the storm sewer. Okay, here's the storm sewer. So the area that gets into this pipe includes this pipe and this pipe, these two pipes. Right? So let's draw the rear lot catch basins. Let's take a look. So the rear lot catch basin, you can see this is the low point, right? You can see all the kind of contours converging, right? Or you can look, let me turn this off. No display. So you can see where, and let me just turn off the drainage areas for a second. You can see the low point, right? This is 593, this is 593, this is 567. So this corner is the low point. So now where does the catch basin go? Well, you have four options. It's either in this corner, in this corner, in this corner, or in this corner. It can't be right at the corner of the intersection. Remember, there might be a fence right on these two lines. So you have to put it inside one of the lots. The catch basin might be here, might be here, might be here, or might be here. And if you look at the PDF, you'll see they always put it in one of the corners, right? If you zoom in, you'll see, right? This is the lot line. The catch basin is inside block 379, right? You can see the corner is here and the pipe is off to the side. So you have to choose one of the corners, okay? There's a couple of kind of philosophies on where you should put the rear lot catch basin. For instance, why didn't they put the rear lot catch basin here or here, right? And connect to this sewer, right? Why didn't they have a pipe coming up this way or on the other side up this way? Okay? And the reason for it is this pipe versus this road pipe, right? These two street pipes, this one is lower. This one is higher. How do I know this one's higher? Well, look at the overland flow. See this fat arrow here, right? It's flowing from here along here. It takes a turn, it goes down this way. This pipe is flowing this way, it turns and it goes this way. So if you look at the profile for Chuchmak versus the profile for this road, you'll find this pipe is a little bit deeper or lower in elevation than this one. So you always want to connect to the low side. Right? So whether you go to this street from the backyards or this street from the backyards is dictated by which pipe has the lower elevations. Okay? So now you know whether you should put it on this side or this side. So in our case, if we go back to the drawing, right, we know that these pipes are higher than these two pipes. How do I know that? Remember, this is the outflow, right? It's going to come up to here, and then from here I'm going to go uphill to here. So now this corner is higher than this elevation. And then if we go in this direction, they're going to be parallel, but this road is always going to be higher than this road, okay, at a glance. And if you look at the elevations, you'll see that on the profile, right? So think about it. Let me show you with my quick sketch, right? Think about the inverts for the storm, right? We're coming out here, come up to there, and then take a turn. I'm going to go up to here. Now this elevation is higher than this. This is higher than this. And now we're going to go uphill, the same slope, uphill, the same slope. This pipe is lower than this pipe. So if you look at them in profile, this pipe would be going downhill, and this pipe will be going downhill, but it would be much higher. So we want to connect, if you look at this cross section, this pipe would be lower than this pipe, right, for the same elevation. So we want to connect the catch basin in the backyard to the lower pipe, not the higher pipe. So as far as this backyard split, we want to connect to these pipes, not these pipes down here. All right, so that's the first thing. So now we know whether we want to put them on north or south of this line. Sorry about the phone. So we're going north for sure. And then it's a matter of east or west, which side of the catch, which corner are we going to use, right? Am I going to use this corner or this corner? And then the thought is, okay, how many lots are draining, right? So if you look at this, let's take this away. Excuse me. Here's the low point, here's the high point, here's the high point. So I have these backyards, and these backyards draining to the low point, and I have these backyards here draining to the low point. Let's turn the drainage areas back on, right? So 1, 2, 3, 4 backyards draining to this point, and then from the other side, 2 backyards draining to this point. So I would put the catch basin here and prevent all this water from crossing this property line. This area, right, there's only one backyard tributary to this. If I put the catch basin here, I have to take flow across this property line and across this property line and then put it in here. If I come the other way, I'll cross this property line once and I'll get into this catch basin just the same. So I don't want to have all this accumulated flow crossing one more time. I don't want to cross this one more time, so I'm going to put it here. So basically, when you look at it, if this is your low point, put the catch basin on the longer swale, swale catch basin side, right? So all this flow, pick it up before it crosses one last time. And I would do that throughout, right? So if we look at the next one, right, the low point is here, right? So I would put the catch basin right here. If I look at the next one, the low point is here, I would put the catch basin right here, and so on, right? Always catch the flow before it crosses the property line one last time, and take the majority of the flow and catch it before it crosses a property line one last time. Now, if the flow is the same, right? If you have 2 lots and 2 lots, then it doesn't matter. It's kind of the flip of a coin. And even what I said really doesn't matter. It could be on one side or the other, but that's my take. I always try and take the majority of the flow and prevent it from crossing one last time. Because now you're getting water in this corner that doesn't come from this lot only. It comes from 2 other backyards, right? So if you put it here, there's 3 backyards coming to this point. If you put it here, there's 2 backyards coming and only 1 crossing over to get there as well. So the total will still be the same. It's still the entire area, right? 0.1 hectares, but a bit of logic to it. Really, it doesn't matter, right? You could put it here or you can put it here. I like to put it on the high side before it crosses one last time. So where does the catch basin go? Well, if you look on Chuchmak, it gives you some dimensions. So let's look at the profile. Where do they put the catch basin? You'll see the catch basin. It's not dimensioned, but I'm going to tell you. The center point of the catch basin, this point right here, is 1 meter from the backyard, okay, and 0.6 meters from the property line. 1 meter from the backyard and 0.6 from the property line. So what does that look like in AutoCAD? If I want to find the center of the catch basin, I'm going to say offset 0.6. So there's the actual pipe that takes you to the street. And then offset 1 meter, there's the center of the catch basin. So I can trim it right there. And that's the center of the catch basin. You want to draw a catch basin, I'm going to make a copy of this line so it's parallel. I'm going to offset it 1 meter. Bring it here. Offset the back, draw a line perpendicular. Offset that 1 meter, and I get this 1 meter square. Close. It shouldn't be wide. Width of 0. So there's my catch basin. 1 meter by 1 meter. It's schematic. Do you want the catch basin to be parallel to the side yard? I'm going to draw a line from here to here so I can find the center and move it to here, and there's your rear lot catch basin. And there's the pipe that takes you to the street, so I'm going to extend that to the sewer on the street. And that's the pipe that's going to be designed by this area. Okay, the next low point is right here, so I'm going to offset by 0.6. Offset from the backyard 1 meter, there's the center of the structure. And if these lot lines are all parallel, I should be able to make a copy of this from the end point to the end point. And there's my next pipe. And its design is based on this area, 0.1 hectares, and so on. Offset 0.6, 1 meter, trim it. There's the center of the structure, make a copy of the structure, end point, and then the same thing here. Offset 0.6, 1 meter, trim it. There's your pipe. Make a copy of the structure. This is all AutoCAD. I'm not using Civil 3D pipes for this. This is just AutoCAD. And then extend to the storm sewer on the street these backyard pipes. Extend to the street sewer these backyard pipes. Oh, I want to do it. Sorry. Turn this off. Extend to the street sewer this pipe. Street sewer this pipe. And you can put them on the same layer if you want. Again, these are not going to be digitized. Okay, I'm just showing them to you schematically. So if I look at my storm sewer now, it includes these leads, right? Backyard, backyard, backyard. Oh, and I missed one. Match properties. And look at it again, and there's my 4 backyards, right? These 2 catch basins connect to this street sewer, and these 2 catch basins connect to this street sewer. And that is kind of a preview as to what I was starting to say earlier. The areas, if we bring back my drainage areas for storm, my storm drainage, what they've done in the drainage area plan that you see for the rest of the subdivision is they've combined all this. So if I look at these sewers with these drainage areas, what they would say is, okay, these two areas combine with this area. That's the total area that goes to this pipe. So then what they do is they basically eliminate these divides, right? They get rid of these. They trim this out. And now you have a total area. So this bubble and these two backyard bubbles get combined. And now you have the total area to design this sewer pipe. We don't design these, and I'll do a calculation as to why that's done. Okay. So now we're going to combine all the backyard areas to the area that it goes to the street sewer. We're only going to put street sewers on our drainage design sheet, right? On the storm design sheet. Okay. Let me undo that so you can see it. So you need to combine these two areas with this street area. And over here, you need to combine these two areas to the area that goes to this pipe. You still need different areas if you have different runoff coefficients. That you can't change, right? Different runoff coefficients, you need different areas. But if the areas have the same runoff coefficient, you can combine them into one. And in this case here, these two areas can combine with this overall drainage area and have one total area that has a runoff coefficient of 0.5. So we could take 44 plus 10 and call it 64. 0.64 hectares at 0.5. And then we have all the information we need to design this pipe here. Why not designing this pipe and this pipe? That's the question. And that's what I want to go through next. Okay. And that's the drainage area that's presented in this subdivision, right? Notice there's no area for this one, right? There should be an area for this pipe. It's not there. There should be an area for this pipe. It's not there. There should be an area for this pipe. It's not there. The area going to this pipe and this pipe and this pipe are all combined into an area that is used to design the street sewer only, 77 to 76. We're designing this only. This is the only line that shows up on the spreadsheet. Rear lot catch basin to this pipe, rear lot catch basin to this pipe, rear lot catch basin to this pipe is not on the spreadsheet. Okay, they combine them and they only design the street sewer. All right. Now we're going to go through a hand calculation. So get out your calculators and we're going to do a calculation and I'm going to demonstrate why they don't waste their time designing the rear lot catch basins. Right? What size and slope should you use in the backyard? I'll show you what they're going to do and why they never show it. Okay, any questions? Does everybody understand what they do? I'll explain why. That's the next part. It's important to understand. In Richmond Hill, they don't do that. In Richmond Hill, you have to show the flow going to this pipe, the flow going to this pipe, and the flow going to this pipe, and the areas for each. That's why I asked you to do it the way I did. So the way we delineated it, one area for each pipe, is what they do in Richmond Hill. Okay? If you start with that, it's easier to combine areas than to try and combine them on the fly, the way that it's finally shown in Milton. So that's why I asked you to do this. Two reasons. One, now you're trained, you know how to do this in Richmond Hill when they want the information for each pipe. If you need to combine them, it's easier to add them together than it is to kind of add them up on the fly while you're delineating the area. Okay, any questions so far? Okay, so let's look at this. We're going to do a calculation for one of the areas, okay? And we're going to look at the worst case scenario every time. So let me do this. I'm going to do this with an overhead shot. So I'm going to do a hand calculation. So get out your calculators. Help me with the numbers. First of all, we want to calculate the Q. I want to calculate Q actual. And if you remember this from MPT, and if we look at the standard, let me bring up the standard, which is Town of Milton. Okay, so if we look at the Town of Milton standard, it's going to tell you how to design the storm. It's going to show you right here, right? So this is the expected flow. So Q actual is going to be defined by this formula here. 2.78 times C, the runoff coefficient, times I, the intensity, times A, the area in hectares. Okay, so that's what I've got here. All right, 2.78 times CIA. Okay, now C is the runoff coefficient. I'm going to use the worst case scenario for our subdivision. So what's the biggest C we have on our site? What's the biggest C value? We have singles and we have townhouses. So what's the biggest C? That's right. So we have 0.75 for townhouses and 0.5 for, we have 0.5 for single detached. I'm going to use the worst case, right? So 0.75 is going to produce a higher Q actual. So let me use the worst case scenario. This is the worst case on our site. If we use 0.5, we know that the Q actual is going to be less, right? Instead of 0.75 here, we're going to use 0.5. Let's look at the worst case scenario, okay? Let's also look at the intensity. So the intensity I, it says that we should design the sewer. We should design the sewer for it tells you, I believe it's the 5-year storm. No, not streets, benchmark, sorry. It tells you that the rainfall intensity, the design frequency is the 5-year storm. So to design for the 5-year storm, we need to determine the rainfall intensity. The rainfall intensity is a formula that looks like this. Remember I, this is going to be the 5-year. It's going to be a formula that looks like this. A divided by T naught plus B to the exponent C. Does this look familiar? And we talked about the ABCs for the runoff coefficient. Well, the ABC, A, B, and C for this intensity comes from an appendix. And the appendix is Appendix D. And it tells you where to look for that. It says here, reference Appendix D for IDF equations. So then we go to Appendix D, which I happen to have a copy of. I think Professor Neruzzi already posted this. So there's your Appendix D. And what we're looking for is not this table, but table number 2. So for the 5-year intensity, and I'm only going to look at this part, there's your A, your B, and your C. So I'm going to write this down. So I, for the 5-year intensity, the top part is 959 divided by T plus 5.7 to the exponent 0.8024, 0.8024. So I'm taking those values and now I'm looking at this, right? A, 595, B, 5.7, right? I'm adding here. And then C is the exponent 0.8024. Those are my A, B, C values from the appendix for the 5-year storm, okay? That's what we're designing for. So that's how you calculate intensity. And there's the formula again in millimeters per hour, okay? The correlation coefficient, it's so close to 1, I'm going to ignore it, okay? So don't worry about that. Assume it to be 1. It's close enough. Let's go back to our hand calculation, okay? So here's the intensity. Calculate this, and the start time, let's go back to the standard. The start time is 10 minutes. So the first T, the top end of the system, the dead end part of the system, the first manhole at the top, starts at 10 minutes. So then we can calculate this based on T. T is equal to 10 minutes. So what's the intensity? 959 divided by T, the start time, 5.7 to the exponent 0.8024. What's this equal? And what are the units? Yeah, good. Brian, you got it. Trong, the units are important too. So this is 105.25 millimeters per hour. So now we know the intensity, right? So now I have C and I have I. Okay, so I have C and I have I. So I'm going to plug those numbers into the Q actual. Okay? So I have C and I have I. So I is equal to 105.25 millimeters per hour. I'm going to erase the calculation. I just need the final answer. Okay, but you can always review this on the video. So now I want to calculate A, or determine A. Now, instead of looking at my drawing, I have an A that's 0.1, I have an A that's 0.1, I have an A that's 1.1, I have an A that's 1.12, and so on. Forget that. I'm going to leave that alone. Okay? I'm going to go backwards now. Let's rewrite the formula. Q actual is equal to 2.78 times 0.75 times 105.25 times A, the area. So if I had the area, I can calculate the Q actual. Agreed? If I knew the area, I have 4 of them, I can calculate the expected flow, the Q actual. I'm going to stop there. I'm going to leave this equation like that for now. And now what I want to do is calculate not Q actual, but the capacity of a pipe. The capacity of a pipe. I'm going to look at a pipe capacity. To calculate the pipe capacity, I need Manning's equation. And to calculate the capacity and the velocity of a pipe, I always need 2 pieces of information. I need the size and I need the slope. So I need the diameter and I need the slope, the percent grade. Okay? I need to know a size and a slope. Let's, for example, look at a 250 millimeter diameter pipe at 1%. 1%. What's Q and V for 250 millimeter pipe at 1%? That's what I want to know. Now you can look it up on a table if you want to. So if you go back to here, remember this. I think Professor Neruzzi gave you the where is it here? The where is it? He gave you that table. Oh, I think I have it on my desktop. Hang on. MED, and we downloaded. If you remember, Professor Neruzzi, I believe, gave you. Where is it now? Remember the one that has the pipe size and slope table? I did this in the sanitary. Oh, it would have been downloaded. No, where did I put it? I showed it to you last week. I forgot where I had it. Archived. No, where did I put it? Oh, it's probably on. MED. Oh, where did we go with it? No, oh, I forgot where we put it. From the table. Okay, you can do that from the table. There, you can calculate it using Manning's equation. Okay, so let me just show you Manning's equation one time. To calculate V, you take R to the 2/3, S to the 1/2 divided by N, where R is the hydraulic radius, S is the slope, N is the roughness coefficient. You might remember this formula. Oh, sorry, you're not looking at my screen, right? So V is equal to this, and then Q is equal to V times A. I hope this is all sounding familiar. And the wetted perimeter, the area divided by the wetted perimeter is the hydraulic radius. So if you recalculate these based on a circular pipe, you'll get V, there's V, V is equal to the diameter over 4 to the 2/3 S to the 1/2 divided by N. And then if you multiply that by the area of a circle, you'll get Q is equal to this times the area of a circle. Q is equal to V times the end area of a circle. Okay, so you might remember all this. This is the formulas you're going to use on the spreadsheet. Okay, you're not going to use that table that you used, table 2, Tron. I don't want you to use a table. I want you to calculate this. So let me go through the details of this calculation at least once. Okay, so if this is the V, and this should be review, but I'll go through it anyway. If this is, I'll do Q in a moment. The diameter over 4 is the wetted perimeter. R is equal to the end area divided by the wetted perimeter, which is the circumference. So the area of a circle is pi r squared. Pi r squared. The wetted perimeter is the circumference, 2 pi r. And if you cancel everything, you'll get r divided by 2, which is the same as d over 4, the diameter over 4. And that's what I put in here. Okay, sorry for the shadow, right? Diameter divided by 4, diameter divided by 4. This is how you calculate the velocity, right? So when you take the diameter, this has to be in meters. You take this, the roughness coefficient for either PVC or concrete pipe is always 0.013, and then the slope is in meters per meter. So a 250 pipe at 1%, sorry, not 1%, 0.5%. I'm going to use 0.5%. Sorry, can you look that up again, Trong? 0.5%, not 1%. 0.5% pipe. But I want to show the calculation gives you the same information. Okay, so then we're going to plug this in. 0.25 in meters, so the diameter is 0.25 divided by 4 to the exponent 2/3 times the slope in meters per meter, 0.005, half, and then we divide by 0.013, which is the roughness coefficient. Okay, Trong, so what did you get for the velocity from the table? And what do you get for this calculation? And this is going to come out in cubic meters per second. Cubic meters per second. Sorry for the blurriness here. Cubic meters per second. So somebody calculate this, and Trong, since you've done it once, can you look up the value on the table? Okay, 0.87 or 0.86. Yeah, that's exactly what I get. So this equals, let me write it up here. The velocity is going to be so the velocity is 0.87 cubic meters per second. Sorry, meters per second, not cubic meters, meters per second. Meters per second. Okay. I calculate it to be 0.86. 0.86. So somebody verify the math, and then you have the table to double check. Yeah, 0.86, 0.87. So that's the value that I get. Whoops, sorry about that. That's the value I get at 0.86, exactly what T has there. So you can always check your calculation by hand against the table, okay? But don't use the table to do your hand calculations. Okay, don't use the table to do your hand calculations. Now that I have the velocity, and you want to keep T, you want to keep that in your calculator memory, so you don't have to calculate it again. Okay, so then what you want to do is calculate the capacity. So the capacity looks like this. For Q, this is V. Now we want to multiply by the end area. The end area again is pi r squared. Whoops, pi r squared times this number here. Sorry, we want to take pi r squared. That's the area, right? Because V times A gives me Q. So let me erase some of this. Now we have V. So we're just going to leave it down here. I'm running out of space. So I know now that the velocity is 0.86 or 0.8566. To calculate Q, I take V times the end area is equal to V times pi r squared, or if you convert that to diameter, Q is equal to V times pi. R is half of the diameter squared. And that's how you can calculate Q, the capacity. This is the capacity of the pipe, right? Capacity. So what's the capacity of the pipe? What's Q? So I know V multiplied by this. Remember, this is in meters. Give me 3 decimal places. T, 3 decimal places. 0.042 cubic meters per second, or 42 liters per second. If you divide by 1,000, or if you multiply by 1,000, you get liters per second. So the capacity of this pipe is 42 liters. Oops, 42 per second. 42 liters per second, or 0.042 cubic meters per second. That's the capacity, right? And the velocity is 0.86, but I'm more interested in the capacity. So this is the capacity. Now I'm going to reverse engineer the area. Remember this formula right here, Q actual? I'm going to make the actual area, the actual flow, equal the capacity. I'm going to make these two equal. I'm going to solve for A. So if I take in cubic meters 0.042 cubic meters per second and make it equal to 2.78 times 0.75 times 105.25 times A, I can solve for A. What is this formula going to give me? It's going to give me the maximum area that you can fit into a 250 pipe at 0.5%. Right? I'm kind of reverse engineering the area. So instead of typing in the area all the time and comparing it to the capacity, I'm going to make the area. I'm going to find out what area produces a flow that's equal to the capacity of the pipe. Right? So if I make this calculation equal the actual capacity, and then I can solve for A, and that'll tell me this is the largest A that you can fit into a pipe that's 250 millimeters at 0.5%. So what's the area? And this is going to come out in hectares, as long as this is in cubic meters per second. What's the area here? Hectares. Give me hectares. Multiply. So did you use this at 0.42? So this should come out in hectares. 1.96. 1.96, is that correct? Hectares? Somebody want to check that? Let's double check. I'm just going to do the math. All right, if I take 914. If I take 1.914, and I multiply by 2.78, and I multiply by 105.25, and I multiply by 0.75, I should get 42 liters per second. I get 420. So make sure your decimal place is in the right spot. 0.042 divided by 2.78 divided by 0.75 divided by 105.25. And we should get, let me just check my notes, I've done this before, we should get 0.19. We should get 0.19 hectares. Whoops, hectares. So this, sorry, so this has to be in liters per second, my mistake. Has to be in liters per second. Sorry, this gives me liters per second, so 42. 42 liters per second. 2.78 times 0.75 times 105.25 times 0.19 will give me 42 liters per second. Yep. Okay, sorry, so this has to be in liters per second, my mistake. Right, now let's look at the town standard again. I think I got the equation wrong. If I look at the town standard, the flow Q comes in minutes, runoff coefficient, length, oh, sorry. So Q, yeah, I believe Q here is in liters per second. Okay, so we're reverse engineering the size slope to determine the maximum area. So as long as none of the areas are bigger than 0.19, I know that a 250 millimeter pipe at 0.5% has a capacity to take this much area. As long as the area is less than this number, then I know that this size slope combination is always going to work. So look at our areas. This is less than 0.19, this is less than 0.19, this is less than 0.19, this is less than 0.19. So without any further calculations, I know that these four pipes, 1, 2, 3, and 4, are all going to be designed as a 250 millimeter pipe at 0.5%. It has the capacity. It has the capacity to take the flow. Whoops, sorry, everybody. I'm getting personal messages here. Sorry. Turn off my phone. My apologies. Okay, so that's what that's how they do the Wow, sorry about that. So that's how they pick up the size of the flow. They know that the maximum area, as long as you don't exceed the maximum, you'll see that the minimum pipe size, 250, with a slope of 0.5% will always do. Now, if you make that pipe, any one of those 4 pipes, if you make them bigger than 250, they have more capacity. If you make them steeper than 0.5%, they have more capacity. So without designing each individual one, right, by each area, right, what's the flow based on 0.1, what's the flow based on 0.1, what's the flow based on 0.12, 0.11, and so on, they just say, look, if we determine the maximum area for a generic size of a 0.5% slope on a 250 pipe, as long as we check the areas are less than 0.19, we know that that size is going to work everywhere. And look at what they did on their design. This is the drainage area, right? Look at all these pipe sizes. A 250 at 0.5%. A 250 at 1.3%. That's steeper than 0.5%, so that will do. This one, a 250 at 0.5%. This one here, a 250 at 0.5%. This one here, a 250 at 0.5%. As long as it's at least a 250 pipe with at least 0.5% slope, you can take an area of 0.19 hectares. Okay, so if you check all the areas going to these individual pipes and they're all less than 0.19, then you know that that generic size, 250 at 0.5%, will work. As a matter of fact, if you look at the entire subdivision, if you go to the entire subdivision, if you go to the general model, you go to any of these rear lot catch basins, and they're throughout, right? These are all rear lot catch basins. Look at the size, right? This is a 250 at 1%. That'll work. 250 at 0.5%. 250 at 0.5%, 250 at 0.5%, and so on. Okay, now why are they not checking them? How come they're not showing that all the areas are less than 0.19? Because they know based on the grading in the backyard, you're not going to get an area bigger than that, right? These are split draining lots versus split draining lots, right? So there'll be an area between these two. There'll be a high point between these two catch basins, and there'll be a high point between these two catch basins. And only half of the lot approximately is going to come to this area, and you can look at it, and you'll see this with experience. It's hard to tell from here. You'll know that the area back here is nowhere near the 0.19. It'll be close to about a half or 2/3 of that. And remember, I'm being conservative, right? Go back to the calculation. I'm being conservative. I'm using 0.75. In reality, most of my subdivision is 0.5, which means you can take even more area, right? Instead of using 0.75, I can use 0.5 for the single homes, and I can actually take a larger area. And most of this site is residential subdivision, single detached lots, right? If you look at this, whoops, not Chuchmak, but if we look at the general plan, most of this are single detached lots. The townhouses are mainly kind of clustered in here. There's a few here, there's a few here, there's a few up here, but most of it is single detached. So I'm being conservative using 0.75, right? I'm being conservative using this number here, 0.75. In reality, it's less, which means this area is actually greater. So basically what you do is you convince yourself that the generic size you want to use, a 250 at 0.5%, will do for any rear lot catch basin. Okay, so this calculation, and some of the stuff I erased, right? This calculation you would keep in the project file. It's a hand calc, right? You would keep this in case somebody questions it. Why aren't you showing me, each individual pipe in the rear lot catch basin area? Because the areas are all smaller than 0.19, right? Or if you choose to be a little more, a little less conservative, use 0.5 for this number, you might get a slightly larger area here. Actually 1.5 times, then you'll see, so instead of 0.2, it'll be like 0.3. You'll know that based on this calculation, none of the areas are going to be greater or anywhere near this number. So you can prove this to the municipality and show maybe 1 or 2 areas and a pattern that they're all less than this. So a 250 everywhere will show. Otherwise, think about it. On the design sheet, for every rear lot catch basin, look how many we have. 1, 2, 3, 4, 5, 6, 7, 8. There's almost more pipes coming out of the backyard to the street than there are street pipes. So the design sheets will have a lot of information on them when it's not necessary. because all of these pipes, the area tributary to each catch basin in the backyard are all less than that maximum we just calculated. 250 and a half, 250 and a half, 250 and a half. We know that's going to work. Okay, so anything bigger and steeper will be even better. And you saw a couple of examples of steeper, but generally they're all 250s. Okay, does everybody understand that process? And that's why in Milton, they don't show the drainage area for each pipe in the backyard. They only show it for the street. So now that you've got your drainage areas, right? Now that you've got your drainage areas, you need to combine them, right? So these two have to be added to this. One area to design just this pipe. And these two need to be combined to this area. One area to design this pipe, and so on. Okay, you can only combine areas that have the same runoff coefficient. But you should not have an area for the rear lot catch basin pipes. Okay, is that clear? Does everybody understand? Any questions about that? We'll go back to the chat. All right, any questions about that? So now that you've done it, so do we need to adjust the drainage areas, or can we just add them together? You need to redraw them. So now in this drawing, instead of having 3 bubbles, 1, 2, 3, I'm only going to have 1 bubble. So I want you to add up the areas and show just one area. And same thing here. Instead of these 3, you add them together, or you redraw it and get the new area so that you don't run into like, look, watch, I'm going to do this. Copy these 3. I'm going to put them over here, right? And I'm going to, I'll do the same technique I showed you before. I'm going to explode these. I'm going to delete the lines I don't need, right? And then I'm going to use the boundary command, BO for boundary. Pick a point inside, and I redraw the area. And that's what goes here instead of this now, right? That's gone. Match the property so that it's the same width and so on. Move it, put it back where it belongs. Right? I'm going to put it here, right? So now it's one area, right? I can delete all these pieces. And be careful. And I think I will demonstrate that it's different. Watch, if I list this, it's going to tell me that it's 0.65, right? If you round that to 2 decimal places, if you divide by 10,000 and round it to 2 decimal places, it's 0.65. What does this add up to? 44 plus 10 is 0.64. If you actually draw it, you'll find it's 0.65. It rounds up to 0.65. All right, so then I would get rid of this. I would get rid of this. I'll change this to 0.65. And now these are the numbers I'm going to type into my spreadsheet for this area that's tributary to this pipe. And then you need an area larger than 0.19. Michael, I'm not sure what you mean by that. No, you don't need an area. You don't need an area that's 0.19. That 0.19 is a separate exercise. Now I know that because these two areas were both less than 0.19, I don't need to demonstrate the expected flow in these two pipes. I know that those pipes, 250 at 0.5%, are going to be fine. Okay, so you need to combine the areas. The backyards that are ultimately going to the same street pipe need to be combined with the area of the street pipe, provided they have the same runoff coefficient. Right? So let me do it one more time. I'm going to make a copy of this. Copy these 3. These should be combined. I'm going to explode them. I'll delete the common lines in between. Oops, I'm going to trim that. Delete that, delete this, use the boundary command. Match the item so they get the same thickness. Move this into position. I'll choose this reference point. Bring it in here. So again, I'm going to delete these. And I have one overall area now. I'm going to list it. Oops, list it. And the area is 3.8, right? So 3.8 instead of 16. So do the math. If you calculate 0.16 plus 0.11 plus 0.12, is it 3.8? It's 3.9. But when you draw it, it's actually 3.8. So I would go with the drafted version because there's a rounding issue. So I would use 3.8 based on the total polyline area. And I would get rid of this, and I get rid of this. And now I have the area that's got this runoff coefficient to calculate and design this pipe, and so on. So now, If you have 8 pipes, there should only be 8 areas, except for the ones that have more than runoff coefficient. Okay? And only these interior pipes need to do that, right? These areas out here, these, we're not going to combine them to what's happening here. Okay? We're not going to redraw them and combine them. We're just going to add the numbers on the spreadsheet. I'll show you that when we do that a little bit later. Okay, so review the marking scheme for the previous assignment. Okay, if there's anything you can't figure out based on the discussion we had earlier, then send me an email and we'll set up a meeting, hopefully tomorrow or Thursday at the latest. If you can, or when you're done anything like that, combine the areas for the rear lot catch basins the way I showed you. So now you're going to redraw some of the drainage areas for your storm sewer. And then you can start to get your storm sewer design sheet in order. Okay, and I know it's getting late, but I just want to leave you with this one thought. Remember the way we did the sanitary sewer? We took the sanitary sewer. Where's my desktop? We took the sanitary sewer. We did the sanitary sewer. Remember we digitized Chuchmak? For the sake of determining how to calculate this, remember? I said recreate the spreadsheet for the 2 sewers on Chuchmak. Remember, 56 to 57, 57 to 58? Recreate the Chuchmak storm sewers. There's only 2 of them, right? So if we go to the storm sewer for the files, if we go to the, is it on here? No, it's on my sheet here, sorry. If you go to the storm design sheets, you're going to find 2 sewers on Chuchmak, and they are near the end, I believe. Yeah, so it's on page 7 of 11. The sewer is 77 to 78 and 78 to 79. Okay, if you can recreate this, right, and calculate everything, then you can use the formulas to cut and paste and calculate what's going to happen on the spreadsheet. This is all input. So you type this in. This is all calculated. This is all calculated. This is input. The length and the slope is input. The size is input. And then this is all calculated. Okay, so let me highlight these. The inputted values are here. I'm going to highlight them. You're going to input all of this. You're going to input all of this. You're going to input all of this. So these numbers have to be typed in. Oops, sorry, my mistake. Let me undo that. Did that wrong, sorry. These you type in. These you type in. These you type in. These you type in. The numbers you type in, and so on. So these are all typed in. Everything else is calculated. These are typed in. Everything else is calculated. Okay, so everything that I didn't highlight has to be done with the formula. Oh, this would be typed in at the beginning. They're starting at 15 minutes. I don't know why, but use that instead of 10. That's what they're doing. So if you can input everything highlighted on this sheet for Chuchmak, there's only 2 sewers on Chuchmak, 77 to 78, 78 to 79. Type all this in, type in everything that's highlighted in yellow, and calculate everything else for these 2 pipes. Then you'll have the formulas you need for pipe capacity, pipe velocity, time of flow in the pipe, A times C, accumulated AC, intensity, and expected flow. So these are the expected flows, Q actual, and these are the pipe capacities right here. So you compare this to make sure that there's enough. In class, the first thing we'll do next week is we'll modify these areas to include the backyard. So we're going to add to these areas at the appropriate location, these areas from the backyard, and see if it has an effect. You can try it on your own if you want, right? But recreate the spreadsheet to do the math for you, and then together we'll analyze whether I can take these areas through those pipes on Chuchmak. Okay, so look at this again, right? The highlighted values are typed in. The non-highlighted values for these 2 pipes on Chuchmak are calculated. If you can get that ready for Tuesday, and if you want, you can start your pipe design for storm, okay? At least the hydraulic calculations. Figure out your sizes and your slope for all your street sewers inside the subdivision. Okay, and that's where we'll pick up next week. Okay, sorry I've gone overtime here, but I spent some time with the assignment review. Okay, so that's it for today. You can review this video. It should be uploaded, if not late tonight, tomorrow morning for sure. And get your storm sewer design going. Again, there's a lot more work to do for the storm, but we'll get through it. Okay. Oh, sorry, we have another hour. My mistake. My brains are crossed. Sorry. Let's keep going. Sorry. You want to take a break, Brian? Should we take a break? Let's ask the question. Let's take a quick break. Let's take a break. Yes or no? You want to take a break? Okay, majority rules. Most people want a break, so let's take a break. So I'm going to go back to share here, and I'm just going to write a note. So back at, let's say 3:20, 3:25. Okay, and we'll continue then this design discussion. Okay, we're back. Sorry about that. I don't know why I thought we were ending at 3:15. My apologies. I've got my spreadsheet started. So this is what I expect you to do. So if when you look at the PDF, okay, and what you want to do is see where these numbers are coming from. Okay, and this is some of the stuff I said earlier. All the numbers you see input on the spreadsheet on this side, on the left side, okay, are going to be from the drawing. Okay, and if the number is on the spreadsheet, you should see it on the drawing. Okay, so let's just verify that. So if we go to the drawing, I'm just going to look at this half here, right? The maintenance whole numbers, and we're going to actually put in the same. I'll show you how to number the system in a moment. But if you look at Chuchmak, and if we look at the drainage area plan, oops, sorry, somebody had a question. Oh, I'm not sharing my screen. My bad. Screen, sorry. Here we go. Sorry about that. Okay, so we're going to look at the spreadsheet. So on this spreadsheet, this is the PDF that we have for reference. Everything on this side here, on the left side, is input, comes from the drawing. Okay, so I'm just going to do this. These numbers come from the drawing. Let's look at that. So we'll look at this here. And let me look at the PDF that has the drainage areas. So I'll break this out separately. And we'll look at this. And this is how they mark it, how they check it at the municipality to make sure that it's done correctly. Okay, so from 77 to 78, it looks like there are 1, 2, 3, 4 areas with different runoff coefficients. 2 of them probably could have been combined. See here, they're both 0.5. But if you zoom in on that pipe, 77 to 78, you'll see here, here's maintenance hole 77, and here's maintenance hole 78, right, 78. So there's 4 areas, okay? And here they are. 0.76 at 7.5. So you can see here 0.76 at 7.5. So that's one area. Then up here you'll see this area drains through 0.08 at 0.5. So that's this one up here, 0.8 at 0.5. And then you'll see these backyards drain into this catch basin that drains into this pipe. Now why do we have that area? Because it's a different runoff coefficient than this one. So this is 0.9 at half. 0.9 at half. And then there's this little skinny area right here, 0.02 at 0.25. And that's right here, 0.02, whoops, 0.02 at 0.25. So you can see the 4 areas with their corresponding runoff coefficients. Okay, so the numbers that are input into the table, the numbers input on the table are actually right on the drawing. The maintenance hole numbers on the drawing are right in the table. Okay, so you can do a quick one-to-one mapping. What's on the drawing? It should be on the table. What's on the drawing? It should be on the table. Okay. For the next pipe, you'll see the same information. Okay. This pipe from 78 to 79, from 78 to 79 has 2 areas associated with it. 0.67 at 7.5, this area here, 0.67 at 7.5. And then you'll see these backyards here. These are different runoff coefficient, but it's combined. This one, right? This area and this area and this area are all combined. And the only reason you have two areas is because you have 2 different runoff coefficients. So you should see 16 at 0.5, 16 at 0.5. So the drainage information input from the drawing, you draw that first, you get your areas, you get your runoff coefficients, right? Once you mapped it all out, you bring that into the spreadsheet. Then going forward, to the left, or sorry, from the left to the right, these are all calculated, right? So A times C, that's a formula. A times C, that's a formula. A times C, that's a formula. So that's this column times this column equals this column. And then the next column is an accumulation. So this cell is the previous total plus the current one. So 40 plus 45 is 85. And then 85 plus 57 is 665. And 665 plus 05 is 660. And 660 plus 0.08 is 0.74. So this is an accumulation, just like the sanitary, right? It adds up. Once you have the accumulated A times R, this is what you'll call the weighted average of the different areas with the different runoff coefficients, right? It's like the weighted average of the different area runoff coefficient combinations. That's A times C. If you multiply by I, this is I, right? A times C times I times 2.78 gives you the expected flow Q. So this is all calculated. So now, from this point forward, this column that I've highlighted, the first number in blue here, that's the expected flow. That's what you have to accommodate. Now, beyond that, continuing to the right, is the hydraulic analysis of what size and slope of pipe is going to give me a capacity greater than this number here. Okay, so the pipe size, and again, this is just recreating the sheet, right? They've decided the size comes from the drawing. So if you look at the drawing, you'll see the size and the length. So this is a 95 meter long pipe. It's a 525 at 0.6%. And the next pipe is 110 meters long, 675 at 0.4%. And you can see that information here, 95 at 0.6 with 525, 101 meters, 0.4% at 675. So that is all in the drawing. Now, in reality, the lengths come from what you draw here, right? So the distance between maintenance holes, that gets inputted. The size and the slope actually starts in the spreadsheet. You actually put in a size and a slope here on the spreadsheet and then show it in the drawing as a final solution. Okay, we're doing it a little bit backwards now because it's already constructed, right? So to recreate the sheet, we already know what the size and slope is. We're not going to change it. We're just analyzing it. Okay, so those values are typed in. So again, they're highlighted here in yellow, and then you can calculate everything else, right? So then we can calculate capacity, we can calculate velocity. So this is V, this is Q using Manning's equation. The time in the pipe is just the length of the pipe, right? And the speed, right? So we're using this formula, very simple, really, really simple. If the velocity is equal to d over t, you cross multiply, t is equal to the distance, the length of the pipe divided by the velocity in the pipe. V from Manning's equation, d is the distance or the length of pipe. So there's time, right? So in a maintenance hole, we start at 10 minutes, and then the time it takes to get from here to here is t plus whatever the time it takes to get into this pipe is the distance in each pipe, and then we add that. Now to calculate the next pipe, we start with 10 minutes. Here the time is a little bit greater because it takes time to get from here to here. So the time to calculate this pipe is a little bit bigger. Then we have time through this pipe, so we add that to this total, and we have time for the next pipe and so on. So that's how we get an accumulation of time. And if you look at the calculation, you'll see, right? If you take here the velocity, 154, right, and the distance 95, right, 154 and 95. So if you take the distance is the distance is 95 and 1.54, you'll find, sorry, wrong calculation here. If you take the distance 95 and you divide by 1.54, what do you get? 95 divided by 1.54 is equal to 61.63. This is going to come out in seconds, so we have to divide by 60 is 1.03 minutes, which is exactly what's being calculated here in minutes. Right, so this is in meters. This is in meters per second. We have to convert it to minutes, not seconds, right? So this will come out in seconds. You have to convert it to meters. Whoops, sorry, can't see that. This comes out in, sorry, this is in meters. This is in meters per second. So this is meters per second. So whatever you do here, you have to convert it to minutes. So it comes up to 61 something seconds, so 1 minute. And that's where this 103 comes from. Then the time for the next pipe is the start time. I don't know why they're using 15, but that's what they're using. They're not using 10 minutes. So 15 plus 103 is 1603. That's the time used to calculate the intensity for the next pipe. So as the time passes, the intensity goes down. Okay, and if you look at a distribution, you'll see that over time, the intensity goes up and then it kind of disappears. So this is the peak time. That's usually the 10-minute mark. And then over time, it gets less and less intense. So we take advantage of that. So as the time increases, you'll see the intensity starts to go down. All right. So that's what you need to recreate on the spreadsheet, right? And that's how you need to type everything in. Everything that's highlighted in yellow is input. You type it in. Everything that's not highlighted in yellow is calculated with a formula. So if you can recreate these two lines of design, and I've already done it, here's my sheet. So the blank sheet is available. Everything in gray is the same as what's highlighted in yellow here. I typed in all these numbers and then I calculated this. This is equal to this product of the previous columns, right? The product of the two columns, the product of the two columns. And then this is an accumulation. This is equal to this plus this. And then the next one is the previous total plus the next piece, and then the previous total plus the next piece, and so on. So you do that all the way. When you get to this line here, you want to design the pipe. So now I have A times C. Then I want to calculate the intensity. The intensity is based on this time. So here's where you put in the intensity formula. Remember A, B, C. A is 959, B is 5.7, and then the exponent C is 0.8024. Right, so that's the formula for intensity. If you want to check it, if this is 10 minutes, what was the intensity? Do you remember that number? Brian, I think you calculated it, or Tron, who calculated it last time? If this is 10 minutes, what should this number be? Whoops, what should this number be? Yeah, so let's check it. This is just some quick checks, right? So if I change this to 10 minutes, I should get 101.25 here, or 105.25, and there it is. So I know the formula is correct. Why they started at 15 minutes, I don't know, but I'm going to recreate it that way so I can check the numbers. So when I do this, this calculated value should be the same as the PDF. And there it is, 84.31, and I'm calculating 84.31. Then the flow is just this times 2.78, and there it is. Instead of 278, I'm using divide by 360, which is the same formula. I don't know if you're familiar with that, right? 1 over 360 times 1,000 is equal to 2.78. It's just a different version of the formula. Oops, sorry, let me show you that, right? 1 over 360 times 1,000 is 2.78. So the formula, if you remember, Q is equal to 2.78 times AIC, or CIA, whatever you want to call it. Instead of using this, I use this, which is exactly the same. If you do the math, it'll give you the same value. I'll just double check it. So 1 divided by 360 times 1,000 is actually 2.77 repeating. Right? So if you round it to just 2 decimal places, 2.78. That's where this formula comes from. 360 is actually converting from seconds to minutes and hours. Remember, millimeters per hour and so on. It's a conversion factor because this is in hectares, this is in millimeters per hour, and this doesn't have any units. So this is the conversion factor to make sure Q comes out in liters. Whoops, in liters per second. Okay. So my formula is a little different. It'll come out the same. Let me just check it, right? If I change that formula, instead of using this, I can multiply by 2.78, and I get the same number. It's equivalent. All right, so however you want to do the math. This is rounded, actually, whereas this 0.7 repeating goes on. It's a little more accurate, the 0.7, right? Oops, sorry, you're not seeing what I see. If you use this, right, it does, this is rounded. It's actually 2.777 forever, right? Or 2.78 is rounded. It's close enough. All right. So now that we've calculated Q, the capacity, and I've done it on my spreadsheet, Q, the capacity, sorry, not the capacity, the expected flow. This is Q actual. I need a pipe whose size and slope combination produces a capacity greater than 155. Okay? Now, in this particular case, I have no choice. The pipe is already designed. The size, the slope, the length, it's been designed, it's constructed. The pipe's in the ground. So I'm just going to check it. So here's how you calculate V. Here's how you calculate Q. And again, it's the formulas that we showed before, Manning's equation. This one here, you'll see, you know, the exponent 2/3, the exponent of a half, divide by n, 0.013. Okay, so it's all there. And then this is the capacity, which has the end area. Here's pi. Remember pi? Pi bracket bracket. That's how you get pi. Okay? So the formulas you used on the sanitary spreadsheet for capacity and velocity are exactly the same. The pipe doesn't care whether it's sanitary water or storm water flowing through it. The way you determine velocity and capacity for a pipe is what it is. It doesn't care what's in it. It just cares about the hydraulics of the situation. It's all water, dirty water from a storm, dirty water from your drain. So it's treated all the same for the most part. Okay, so I'm not going to go over that in a lot of detail. It's the same calculation you did on your sanitary sheet. So then what you do is you can compare, right? This capacity has to be greater than this, and it is. And this capacity has to be greater than this, and there it is. So it works. So these pipes are big enough with the size and the slope combination. The size and the combination yields a capacity greater than the expected flow. And again, if you want to, and what I typically do is I unhide this. I typically calculate the capacity. Okay, I don't need these, sorry. Let me just get rid of these. All right, so now I look at the percentage, right? I take this, the actual divided by the capacity, and that tells me the percent full. So the pipe is only 46% full. And this pipe, 280 divided by 532, is only 53% full. So you can see that there's still a lot of room in those pipes to take a little more flow, a little more area. So I'm of the belief, if we go back to the drawing, that whoever designed these storm sewers on Chuchmak, whoever designed these two pipes on Chuchmak, anticipated that maybe, and perhaps in the future, these residential units might be back to back with other residential units. And if that's the case, the designer said, okay, I have area coming to these catch basins. I'm going to kind of double it. Maybe there's some area in the future, if things change, that might bring more area through this road and these two pipes. And that's what I think happened here. The reason these pipes are so big in terms of the requirement, and let's go back to the spreadsheet, you'll see you can actually make them smaller. Instead of a 525, let me use the next pipe size down, a 450. It's only 70% full. Let's try a 375. Oh, that's too small now. So a 450 would have been sufficient. And then the next one could have been the same or bigger. Let's try a 450, too small. The next one would have been a 525. That's tight. How about a 600? Yeah. So instead of a 525 and a 675, I could have saved one pipe size and then captured this flow with plenty of capacity. Now, we don't want these numbers to get higher than 85%. Typically, we don't want the pipes full. We always want a little bit of flexibility. But certainly, these pipe sizes, a 525 and a 675, which was proposed, designed, approved, and built, are way bigger than they need to be. And I think that the designer added the area from our subdivision, right? Decided, hey, this might happen in the future. So let's take some areas, half lot depth back here, and bring it through. Size these pipes, and then erase the area. So imagine that. You add the area, you make the pipes bigger, and then you don't show that that additional area is actually coming in. So at a glance, it looks like, you know what, your pipes are too big. It doesn't make sense. You can make them smaller. But he was forward thinking, or she was forward thinking and saying, you know what, maybe in the future, So, but why make it larger for the future? Wouldn't it cost more money? One pipe size is more expensive for sure, right? The bigger the pipe, the more expensive it is. However, if you had to replace that pipe in the future, if things change to the south, then it would be a much more expensive cost. Reconstruction, dig up the road, take out the old pipe, put in the new pipe, right? It would be a disaster from a cost perspective. So to put it in a little bit bigger now, in anticipation of maybe this might happen, is a little bit forward thinking. Now, you know, you may not have to do that, right? And nobody's going to tell you you need to do that. However, I think in this case here, that's the case. That's what happened. They actually decided, you know what, maybe this won't go commercial. It'll maybe go residential. In fact, it didn't, right? When I showed you the Google Earth image or the Google Map image, it's not. It's actually a commercial property. So this never happened. But I think they hedged their bets, not knowing. Remember, in the subdivision, and look at the drawing, right? Not part of the subdivision. Who knows what's going to happen here until it happens. So what did they do? They designed it for the worst case scenario. The worst case scenario is a commercial property. But at the same time, if it doesn't become a commercial property, maybe we should anticipate some back-to-back units here and safeguard having to rebuild or redesign these sewers. So there's a bit of redundancy built in to what actually happened. But however, I think it's not a bad idea. Okay, so should you do this every time? No. Do I know the whole backstory? Do I know the client? Do I know all the details of what's happening here? Absolutely not. Okay, I'm just speculating. Is that something the municipality might insist on during planning? You know what? They wouldn't. As long as you show them what your assumptions are, and that's what they did, right? So if you look here, the assumption is that this entire area is going to come out this pipe, right? Everything's going to come out here. That's the assumption. So based on that assumption, this is all you need to do here. So this was overkill. To make these two pipes bigger than necessary was a bit of overkill. Now, the municipality is going to say, well, you know, those are bigger than they need to be. Is it going to work? Of course. Did you spend more money than necessary? Maybe. But remember, the developer pays for this. So the developer was kind of paying a little bit of insurance up front. In the end, they didn't need to do that. However, in our exercise, it actually benefits. So had this gone as a residential subdivision the way I've proposed it, there's capacity in those two sewers maybe to take these backyards. Otherwise, what would happen is we would have our own catch basins back to back. We'd have a catch basin here, another one here, another one here. It would look kind of silly, right? So I'm going to take more area this way and find out what happens. How much more area? Well, let's look at the drawing, right? This pipe and the pipes are going to go into the bottom end, the last pipe, and these three areas are going to go into the first pipe. So here's what I'm going to do. I'm going to increase the area that goes to that pipe that's a 0.75 runoff coefficient by 11, right? 0.11. I'm going to combine these two and add them to the area that has a 0.75 runoff coefficient. And then the one that has 0.5, there's two of them, I'm going to increase it by 0.5 and see what happens. So let's go back to the spreadsheet. Remember 0.5 and 1.1. Let's go back to the spreadsheet. So I'm going to increase this one by 0.5 and I'm going to increase this one by 1.1. Okay, and I've already set it up to do that. If I want this to increase by 0.5, I put in a formula here. I'm going to add 0.05 times this number. So I'm just going to change this value from a 0 to a 1. Just to get the math to happen quick. Okay, so if I change this to a 1, watch what happens. Watch this number and this number. So this 0.8 is going to add 0.5, which would be 13.13, and this 76 is going to add 1.1, which is going to be 87. Right, ready? Watch. Okay, so 13 and 87. So now I've increased the area going to this pipe. What happened to the capacity? Well, this number goes up, right? The expected flow is bigger. There's more area. But how does it compare to the pipe capacity? Well, look at what happened to the percent full. So when this is 0, and I'm just playing games with the math, you can actually type the number in, right? You don't have to add it the way I did. But if I take the 0.8 and add 0.5, you get 11. And if I add 7.6, if I add 1.1, you get 8.7, right? So watch this. If I make this 1, watch what happens to the percent full. It goes from 46 to 54. Still plenty of capacity. Now, what if this was the smaller pipe size, 450? Starting to creep up near the 85 maximum that most municipalities allow. So the 450 probably would have worked, but they said, you know what, it's getting close to full. Let's just make it one pipe size bigger, and that should have plenty of room. Same thing with the bottom pipe, this pipe here, right? Let me make this a 0 again. What are we going to do to the second pipe? Well, let's go back to the drawing. The second pipe is going to increase the 0.75 runoff coefficient. I'm going to add to it 0.9 and 0.8, which is 17, right? 0.17. So that's what I did here in this cell. I'm going to add an additional 0.17 by changing this value to 1. So if you add 17 to 67, you get 84. That increases this flow, expected, but not the capacity. And now this percent full goes up. So when I make this 0, before our subdivision took water the wrong way or the other way, this was the pipe capacity, 46 and 53%. 46 and 53%. Add the additional area to those two pipes. It goes up to 54 and 63, which means these two sewers have capacity to allow the north strip of our site to go through. And this is what you have to show the municipality, because that's what you're proposing to do. I'm going to take the backyard of these townhouses, these blue areas, and I'm going to put them through this sewer. And that now puts less area through our site. So the pipe that's here now is probably too big because there's less area going there now. So this is all theoretical discussion when you look at the drainage areas, right? Can I take the area that way? Well, yeah, the geometry works, right? There's low points and catch basins in places that allows that flow. Then I've got a split point, kind of in the middle of all the lots that will take the drainage internally, and then those backyards are going to go to the other part of the subdivision. So it's a theoretical kind of want at this stage, but then you prove it with your calculation, right? So now I've just proven that if I add additional area to these two pipes, the flows increase, but they don't go beyond the capacity of the existing pipe. So there's no negative impact on those sewers. I can do this, and I've proven to the municipality that it's possible without any undue harm to the original pipes. And that's something you need to demonstrate, right? Just because you think it could happen, this proves that it can happen, right? And that's an exercise you would have to do if you're going to reroute any flow to a different originally intended location. So we can do this. I don't have to propose my own catch basins from the north coming down. All right. Any questions about that? It's a very kind of theoretical calculation, but it proves the point. You can't just assume it's true. You have to prove it's true. Okay. You'd have to do the same thing here. These two areas are going to be tributary to the sewers on Ledger Way. So you'd have to increase those areas. So what am I talking about? Let's go back to the drainage areas, right? We've got a little bit of backyard here. That area that I just highlighted is this area here. So there's some more area coming to this road sewer. And then this piece here is the backyard of these lots coming to this road as well, where the high point is. This is the high point on the road. Remember, Ledger Way has a high point, which is this area here. So there's some more area here coming to this. So what would I do? This is 0.75. I would increase this number 0.9 by whatever this little area is that I identified and see what happens to this pipe. The capacity will not change, but the expected flow goes up. So what happens to the percent full? Same thing here, right? This is 15. What am I going to add to it? I'm going to add 0.3. So instead of 0.15, it's going to be 0.18. So if I increase that number by 0.03 from 0.15 to 0.18, what happens to this pipe? Is it going to be big enough still to take this additional area? Same analysis required for this pipe and this pipe. Okay, and you can look at the areas. You can look at the areas to a certain extent. Sorry, where's the drawing? My drawing. You can look at the areas. They're very, very small. They're not insignificant, not like sanitary sewer, right? But 0.02 and 0.03 are very, very small increases. Will the expected flow change? Of course, but they probably won't exceed the capacity of that pipe that's already in the ground. That's my gut feel, right? But you still have to prove it. You have to recreate the spreadsheet and show the increase in area, and then show that this, what was it before, and what happens to it if you increase the flow. It's still within the limit of what's required. Okay, so that's an interesting bit of analysis that happens, right? If you're going to change drainage divides from originally proposed to, kind of a new concept. And it's of particular interest if the pipe that you're impacting or changing is already built, right? I can't change the size. I can't change the slope of those two pipes on Chuchmak. So whatever I do, it better not negatively impact them. Okay, does everybody understand this analysis? It's the same discussion we had with sanitary, but it's more significant. It's more likely that it could have a greater effect. It's not as insignificant as the sanitary, that small little sanitary area that we sent the other way. The storm is a lot more significant. All right. Any questions about that? So I would demonstrate that, show that for sure. recreate, and I do this for two reasons. One, it's something you need to do. It's part of a design requirement. The other reason is a little more practical for this course. The reason I want you to recreate this calculation and check this, right, by increasing the area. Start with this, right, the original design, and then increase the areas, whatever you drew at the north end, right? Your numbers are going to be different. My blue areas and values are all different. They might not be the same as yours. So just double check, they'll be close. So recreate the sheet before you add those areas, and make sure, double check, that these calculated values are the same as what you see on the PDF spreadsheet. And that's just one way of ensuring that your calculated cells have the correct formulas. That's the practical, that's why I'm asking you to do it, right? And then you can copy and paste formulas. Okay? If you did the sanitary exercise, right, this is just the equivalent. Do the storm exercise. And once this is ready, you can use it to do the analysis, right? Increase the areas and demonstrate that the pipe capacities, are adequate. You're not going to negatively impact the sewer. Once that's ready, then you can copy and paste formulas into the proposed subdivision, right, for the inside. And again, the numbering scheme, since we're here, I'm going to isolate this layer. The numbering scheme for here is just like the sanitary. We're going to start at the bottom and work our way up. So let me just redraw this and discuss this. And I think we did this. So I just redrew this. Okay, so this is the existing sewer maintenance hole. If we zoom in, you should see the all the existing stuff. Sorry. So you will see the existing pipe. You should always show the existing pipe for storm. Right. So this one, even though it got shorter in my case, it'll show the existing pipe. And then maintenance hole 76 and 301, 76, 301, right? So this is fixed, 76, this is fixed. Now, even though this is 301, if I move it, I'm still going to call this one 301. And then it looks like this, right? So 76, 301, this is the existing pipe here, right in here. So I'm going to call this maintenance hole 1, maintenance hole 2, and then you should always go the shortest distance first. 2, 3, 4, 5, 6, 7, 8. I think that's what we did with sanitary, correct? Make sure I'm not talking. Right, and this is MH, obviously. And there's no A, right? It's just a number, MH1, MH2, MH3. Okay, these are your sewers. And then each one has an area. Each one might have more than one, like these up here might have more than one tributary area because of the different runoff coefficients. Set up your spreadsheet. Always design from the top down, right? So figure out this size before you figure out this size, before you figure out this size, before you figure out this size. Always design the hydraulic pipe size from the top, work your way down. Why? Because when you change the diameter of the pipe, or you change the slope of the pipe, it's going to change the time in the pipe. So you want to set the time to this point here before you design this pipe, and set the time to here before you design this one, and set the time to here before you design this one. So always design from the top of the system, the dead end at the top, in the direction of flow, always toward the bottom. That way you're not gonna upset the time the sequence. Okay, so if you go to the spreadsheet, right, if you change the length of the pipe, watch what happens to the time. If you change the length of the pipe to 95, to 90, the time changes. And then this time of concentration is now going to affect the next pipe, right? So if I make this 95, watch what happens here. 95, the time in that pipe is used to calculate the intensity of the next pipe. So you want the top end designed first before you design the next pipe downstream. So always start at the top where the flow begins and work your way downstream. Right? So we'll go back to my sketch. You want to fix this design. It's got to be finished. And then you go on to the next one. You got to finish that one. Then you go on to the next one. You finish that one. Then you go on to the next one and finish that one. There's going to be a little bit of, again, remember the solution is always parametric. You need a size and a slope. So make sure to begin with, you remember the minimum slope on the road is all 0.5%. So make all the pipes to begin with 0.5%. Make all the pipes, including the dead ends at the top. In sanitary, we made them steeper. Remember 1%? For storm, make them all 0.5% to begin with, and then just play with the size. Change this size. A 300 is the minimum pipe size. How do I know? Check the standards. So if we go to the standards for municipality, for desktop. If you go to the standard, you'll see that the minimum pipe size to begin with is right here. So the minimum pipe size is not here, minimum size, where is it? It's got to be in here somewhere. I think it's a 300. Here it is. The minimum size for storm sewer is 300. Okay, so when you're designing on your spreadsheet, right, put in a 300 here. Right? If this capacity is bigger than the expected flow, you're done. If not, make it a 375. Does that work? No. Make it the next bigger. Does that work? No. Once you get to the size that works, let's say it's a 450, then the next one, start designing at 450. It can't be smaller. It could be the same or bigger. Type in that size because the slopes are all the same. Type in that size. Once the capacity is greater than the expected flow for this sewer, you're done. So maybe a 525 works for this one. If this is done, the next pipe, start with a 525. Is that capacity bigger than the expected flow here? No, make it bigger. Does that work? Yeah, go to the next one. Start with that size. Does that work? No, make it bigger, 675 and so on, and work your way downhill. Start here, right? Size this one, size this one, size this one. Once these two are sized, then you do this one. So always start at the top and work your way downstream. So start at the dead end. When you get to a junction, stop, wait there. Start at the top, work your way to that same junction, stop. Now you have all the information complete to design the next sewer downstream, and so on and so on. So that's the design approach. Start at the top and work your way down. Okay, and you should see these pipe sizes will probably get bigger and bigger and bigger as you go downstream, because the expected flow for storm are much greater values than what you see for sanitary. Okay, so this is a little more dynamic than the sanitary sewer. Okay, any questions about that? So for homework, and remember I talk about keeping pace all the time. If I taught it, try and get that work done for the next class. And then we can continue the discussion for the design for the next part. Okay, if you get that design complete, right? If you get this design complete, if you want to input this design into the drawing, draw the pipe in profile. Now that you have all your sizes and slopes, you can go ahead and do that. This approach is like last semester, however. Do exactly what you did last semester. Start at the bottom and work your way up. Okay? Sanitary, we did backwards from what I taught last semester. For the storm, start at the bottom and work your way up. Right? So what are we going to do? We're going to pick up the invert at the street, put in the slope of this existing pipe. If it got shorter, you'll calculate a new invert here. And then take that invert, add the minimum drop, go up the pipe at the length and slope, add the minimum drop, go up the pipe, add the minimum slope, add the minimum drop, and keep going. And then whatever you get here for an invert, add the minimum drop for straight through, add the minimum drop for 90 degrees, and then you do the rest of the two legs together. So storm is backwards, or not backwards, is like I taught it last semester. Start at the bottom, use minimum drop, minimum slope, and go uphill. Okay, sanitary we did backwards for a different reason, because this pipe here is already deep enough, so I don't want to make the system too deep. Storm is much more shallow. So if you look at the profile for Ledger Way, you'll see the storm sewer has a typical bearing. It's parallel to the road above, right? So we're connecting to this maintenance hole here. That's our subdivision. Right? So these are our connection points. Our subdivision is right here. Right? So these are the connection points. So what you need is not the invert here. If you move this maintenance hole, you can't use these inverts. They're all kind of given here. Okay, you can't use these inverts. Start with the invert here. Not this one, but this invert. So on this maintenance hole 76, there should be 3 inverts. Right? So there's this invert down here, this invert up here. It's the one in the middle. This is the pipe we're connecting to, this ellipse that goes into the subdivision. So it's not the lowest invert. It's not the highest invert. It's the one in between. So if you go down here for storm, right, it's not the lowest, it's not the highest, it's the one in between. This is your starting invert, right? And then the slope of the pipe is given here. It's 0.5%. So you start with this invert, go up whatever the length is. And again, if you move this maintenance hole, this length, 15 meters, may not apply again, right? So start here, add the length times the slope, get a new invert, add the minimum drop, length times slope, add the minimum drop, length times slope. So work your way uphill, just like you did last semester. So that should be a familiar exercise. You can't do the geometry of the inverts until you know the pipe sizes, because the pipe sizes are going to dictate the match obvert condition. Remember, you have to match obverts, right? The upstream pipe through the maintenance hole, has to match. The tops have to match as a minimum. So you take the difference in pipe size. That's one number to think about. And then you take the difference in inverts based on straight through, 45 degrees, 90 degrees. Remember, straight through, 45, 90. And that information is given in the standard. If you go back to here, you'll see the change in direction. And I believe it's specified right here. So straight through, use 20 millimeters, 45 degrees, use 50 millimeters, 90 degrees, use 80 millimeters, or 0.02, 0.05, 0.8, 0.08. Okay, so this is the minimum drop based on the change in direction. And then there's also the match obvert condition. Right, so this is the minimum, right? And then where is it? Also, it should talk about match obverts in here, I think. Head loss, drops, and should give it here as well. Let me just check, Control F, obvert. Okay, it's not in the standard. I would match obvert as a minimum as well. I don't think it's in the standard. Somebody finds it, let me know, but I don't think it's in there. Match obvert. I don't think so. Okay, it's not a standard, but it's generally accepted that you should match obverts. So again, what's the difference in pipe size? Right? What's the difference in pipe size? That's one minimum drop condition. And what's the difference in inverts based on straight through, 45 and 90? Whichever one is bigger, that's the one that governs. So start here, distance slope, invert, add the drop, distance slope, invert, add the drop, distance slope, invert, add the drop, and so on. So work your way uphill, just like you did last semester. If you can get that designed hydraulically on the spreadsheet, and draw the pipe in plan and in profile using the database for next week and have that ready, then we can finalize the discussion for storm. Okay? There's one more thing that needs to happen, and we'll discuss that next week. Okay? So that's getting started. That's the first iteration. Okay? Any questions? I know I'm throwing a lot at you, but most of it's review. It's stuff you've seen before. Okay, as far as completing the design, once the storm sewer is designed, the rest of the design to complete the design for the submission is some AutoCAD drafting. Okay, the missing information now will be the rest of the street catch basins, draw the water main in the profile. We're just going to use AutoCAD to do that. That won't take too long. Okay, so next week we should probably complete the design discussion for the third submission. All right, any questions? So do we need to account for the storm drainage on Louisiana? We're going to analyze that together. Okay? You can do that if you want, but I'm going to leave that exercise for next week. That's more than enough for now. Okay, so your first iteration should be to design what we have so far. But that's a good foresight, Stephen. I will discuss that next week. Any other questions? Okay. Okay, so I'm going to stop that and I'm going to stop recording.